Hello, good evening all. We will start the session after 2 minutes, after 2 more minutes. Let others join. Okay, so hello, good evening all. Hope you all are fine. And let's start today's session. So I will share the Replit link and you all can go and see the first question. But before moving into that, okay, let me just share the link first. I'm sharing it in the chat box. Okay, so I have shared the link. You all can check in the chat. Uh, can someone respond? Can you all see the question?
Yes, sir. Good evening.
Good
I
evening.
can see.
Okay, thanks. Okay, so yeah, just before reading that question and before going into that, so I just want to ask, so what is the feedback for this week? I mean, we understand that in the middle of this week, 5, 6, mostly week 6 and 7 also, it was a bit difficult. Uh, so how do you feel week 8 as of now?
Week 8 is lighter in terms of previous weeks.
Yeah. So yes, week 8 is a bit lighter than all those weeks. Mostly, see, the problem is in week 5, 6, and 7 is not that much difficult, but yeah, there are some So week 7, the week where we discuss about the greedy approach, right? Week 7. So the main idea in that week is if you can pick up the correct heuristic, everything else is okay. There is nothing difficult after that. Only picking the correct
Yeah, in fact,
yeah,
greedy algorithm,
yeah.
greedy algorithm was,
Sorry, I could not hear you
but if
for 2 3 seconds.
what I said, greedy algorithm was quite an interesting topic,
Yeah.
and even the graded GRPA 2 and 3 were quite interesting.
Yes. Yes. Yeah, so that's it. I mean, in greedy algorithms, you do not have to do a lot of coding from the data structure point of view, not that much, because the main idea is you have to pick up a correct uh, metric or heuristic, whatever you want to say, in order to get the correct result. And main difficulty in week 7 is whether a particular chosen approach to solve a greedy algorithm, whether that is correct or not. So proving that theoretically, that is something which is a bit difficult, and understanding that okay, this is wrong, this is correct. Some approach may seem to be very correct, but that is not actually correct. So all those things, the theoretical part of it and choosing the approach is difficult, but after that the coding part should not be that much difficult like week 6 and week 5. The reason for that is again week 6 and week 5 has hard, I mean a lot of data structure oriented coding. That's why it was a bit difficult. Week 8 is also something like this. We do not have a lot of data structure oriented coding, but mainly the algorithm part, how you can approach a problem. Okay,
So
so
if quiz 2 is on 10th of July or somewhere around that,
yeah.
then can we have a refresher course for week, focusing more on week 5 and week 6 again, at least one class for that,
Okay.
and not like revision for week quiz 2, only focusing for these 2 weeks.
For which weeks? Week 5 and 6, right?
Yes,
Okay. Okay. Uh,
and
so
maybe 4 if any question comes.
okay, fine. We will see that. I mean, we will do that, no issues. So revision week would be around 10th, right? So it would be something around 5 to 7, 8, 9. And so before 5th, we would do one session then. Fine.
Yet, I mean, in a time slot to which we can extend if need be. So maybe towards the evening, late evening time slot.
Okay, fine. Fine. Okay, we'll do that. Okay, so let's come back to what can be syllabus of quiz 2. Quiz 2 syllabus, you all know that. I mean, anything in algorithms, you have to learn all the initial content also, right? And after that, it is up to week 8, right? Up to week 8, I think. Yeah.
Yes.
So week 1 to week 8. Okay, so okay, let me ask this question. So which parts of week 8 you feel a bit problematic as of now? I don't know how much content you all have gone through, but yeah. So these are just means for our own understanding.
Completed 4 till 8.4. Till now,
Okay,
it is okay for me.
okay, fine. Thanks. So anyone else, any specific topic that you all want to be discussed again? Not maybe in this session, because we would not have time most probably. Uh, yeah.
Closest pair actually.
Closest pair of points, right? Okay,
Yes.
fine,
Suppose if they are pair.
fine. Okay, so
Yeah,
maybe
why? Because see,
uh,
everything has been discussed in kind of discussion mode without taking a real example or any coding example. So to how to understanding the discussion is okay, but then putting it on practice,
yeah, yeah,
that
yeah.
is not discussed in the lecture.
Okay, okay. So fine. Maybe not this week because we have the OPP exam. So maybe in the next week we would try to schedule one such. So week 8 one extra session and week 5 6 one extra session. Okay, yeah, that's it. Thanks for the yeah, pointers. Now you all can please check the question out and start coding. Okay, so this is the first question. Let me just tell you a few things before you all start doing the work. So 2 or 3 points. So first of all, you have been given a list, and in that you have to find such a number, I mean the such an element in the list who is greater than its both the neighbors, that is both its left and right neighbor, both it is greater than both its neighbor. Now you can have multiple such occurrences of a number, right? So you can have multiple such occurrences. So your program should return any one of them. There is not a problem with that, but it should work in a log n time. Okay. So any such number who is greater than its left and right neighbor, you can return that, but it should be a log n time algorithm. Fine. The main idea is log n. So see, the main focus of this week is whether how can you how can you cleverly identify a part of a question that you can divide and then work upon that, and finally merging all the sub works, all the divided works, right, the subtasks, then give you a correct result. So in many problems this approach would work, in many problems this approach would not work. So let's say in a graph algorithm, okay, just be with me for 1 or 2 more minutes, then we can again continue coding. So for example, in a graph algorithm, like let's say DFS or any Dijkstra, anything, let's say Dijkstra only. Okay, so in a Dijkstra algorithm, do you think a divide and conquer kind of approach would work? That is, you divide the graph into smaller subgraphs, maybe some subgraphs basically, and then try to find the smallest possible path between 2 points in that subgraph, and then again join that sub or join the other subgraphs and kind of merge the smallest paths in among all the subgraphs, and then you tell that among all these subgraphs I have found the smallest path, and then I'm adding the all the smallest paths, so I should get the overall smallest path among in the whole graph. Do you think this kind of approach would work? So yeah, if you think it would work, you can comment, or you may also totally disagree with that. Either case, you may give some reason. Anything, just a blind guess. Yeah.
So, see, in Dijkstra, we were like taking example of firing of the oil depot.
Yeah.
So we are we are firing at a particular node, and then uh, later we are seeing which other nodes are the fire is reaching first, and from there we are counting. So if we divide the problem, I mean break the pipeline into say two sub pipelines,
Yeah.
then I think it may not be able to give us optimum. Why? Because in one of the things it will give a greater time as a solution of the shortest path, and in the other subpart it will give earlier time as a solution for the shortest path, and then how to combine these two will be a problem.
Exactly. So the division phase would work as you said correctly, but the combination phase would be difficult. The reason for that is, so let's say you find the shortest path in a subgraph, right? And then when you join it, that is fine, that is okay. But when you join it with the other subgraph, right, it may be the case that the edge which joins these two subgraph, or maybe it can be multiple edges. So in the scenario where there is a single edge between the two subgraphs which we are joining, right, in that scenario it would work because okay, so let me just draw it. So what I mean is, in a situation where kind of, let's say, uh, okay, so let's say this was my one subgraph. Just a second. uh, okay, so this was my one subgraph. Fine, there were some edges, and let's say there are some few more vertices over here, dot dot dot, and this was the second edge. Okay, so this means basically this dot means basically there are few more edges and vertices, right? So this is basically my one subgraph, and let's say this was my another subgraph over here. Okay, and let's say like this we have few more subgraphs, and here it is another final subgraph where the target node is there. So that is the last target, the destination. Okay, and let's say this was my source in one of the subgraphs. Now the thing is, you find the shortest path. So let's say some shortest path, right? I'm just drawing it like this, some shortest path from S to this bordering node, which is there inside this subgraph. Okay, this is the shortest path which I have drawn. So fine, shortest path inside the subgraph, inside this subgraph. Now let's say if there is a single edge connecting these two vertices between the two subgraphs in the original graph, I mean only a single edge is there between these two, then there is a possibility that your algorithm, this breaking and merging may work, but that should be the case for all the joining all the subgraphs. That is, between all the subgraphs there is always a single common vertex, and that is joined by a single edge. Fine. Now if that is the scenario, then there is a higher probability. Then also I cannot never always say that it would work, but there is a higher probability that breaking into subgraphs and finding smallest path in each subgraph and finally merging them would work. And the reason for that is quite, I mean, quite intuitive, because there is only one edge. It's kind of a bridge edge. Right? It's not a kind of, it's actually a bridge edge. So if you delete that, then you would not be able to go through that path. So that is the possible scenario. But again, there may be another scenario also where there are multiple paths. So in some of the Dijkstra question, I think one question in the quiz was also there. Sorry, not quiz, in the graded assignment, that where there are multiple smallest path in one Dijkstra algorithm. In that case, you can again have an edge from here to here that may not be considering the bridge edge over here. Okay, so that means even if I have only single edges connecting this subcomponent, then also I can never guarantee 100% that breaking and subdividing and joining would work, because of the reason that I may have multiple smallest path, and let's say this smallest path does not consider that bridge edge. Fine. But in an example where there is a single smallest path and all the subcomponents are joined by a single edge only, then there is a higher probability. Okay, I'm not able to think of any corner case where it would work. Sorry, not work, but most probably it would work. But that also is not something which is provable. But you have so much constraints. All the subgraph must be such that it should be joined by a single bridge edge, right? There should not be multiple smallest path. All these constraints are there. And at the end of the day, by having so many constraints, you are not doing anything much better, because you also know that the complexity of divide and conquer also are most probably something in the logarithmic multiplied by an algebraic term, something like this. And we already know that Dijkstra provides us a e log v time, provided we are using a heap. Okay, so yeah, adjacency list or heap, I mean whatever. So this is the idea. So basically in graph algorithms, dividing and then working does not provide a good output. It's not proper. So that's why that's not usable. So where we can use this divide and conquer approach, that spotting those kind of scenario is something that we want to learn in this week. Okay. So in this question, let's come back to this question. So here you have to spot which thing I can do in a divide and conquer manner. Let me give you one small hint that here you do not need it to be sorted. I mean, it's already, it is given to you that you have to find the element which is greater than both of its neighbor. But that does not mean that you have to sort it or do something like that, right? The sortedness is not required. So you can actually use this jumbled up behavior to do something. Okay, yeah, so please try to do this. So we will wait till 6:32, and then we will discuss.
Uh, Excuse me.
Yeah.
I'm trying to click on the main.py, but the cursor is not coming.
Okay, just a second. Can you try to write something?
I'm not able to write anything.
Uh,
Cursor
Wait.
is not coming at all.
So I think there is some problem. I can write on your interface. Can you? Okay, let me just do one more thing. Can you just do one thing? Can you please go to the previous week assignments? I think those things are already published, right? So they are kept published, I hope. So, and please check the live coding sessions of those weeks. Can you access them?
I'll try that.
Yeah.
No, there also it was not coming. I again rejoined the Ripple link. I don't know what is happening.
Just a second.
Could you please try writing something on my Ripple?
Yeah, I just did that already. It's happening. It's working.
No, but it's not visible to me then.
Okay, just a second. Now I'm writing again. Just a second. Yeah, see whether you can see what I'm writing.
Yes, it is appearing.
Coming, right? Yeah, now I delete it. I can see your cursor, but okay, fine.
I'm writing something, but is that visible? No.
No.
Yes. I can only select lines, but then cursor is not coming on that line.
Yeah, maybe there you can change your browser or something next time. I
I'll
don't
try.
know. There should be some problem.
I'll try.
Okay, so let us discuss this at first. First discuss the approach and then we will go to the coding part. Okay, fine. So let us discuss it over here. Fine. So let's see what the question is asking us. So we have a list, a random list. Let's say 2, 6, 9, 4, 0. Fine. So let's say this is the given list. Okay, and we need to find such a number which is greater than both its neighbor, that is left and right, both its neighbor, right? I hope you all can see the screen, right?
Yes, sir.
Okay, thanks. So we have to find such a number which is greater than both its neighbor. So what are the possible ways to do that? Let us now, since we are at week 8, so we have some knowledge of multiple approaches of solving a problem, right? So what all can be done? How can we proceed?
No, without looking at login constraint, it is quite simple to do this.
Yeah. I'm not talking looking at login, just normal, any approach.
You can divide the list and search for actually.
Sorry, can you be a bit louder?
You can divide the list actually. can split the list and you can search for the peak in the each list, and you can finally search the peak in the combined list, like a merge sort.
Okay, so what would be the complexity for that?
Maybe n log n.
What?
N log n.
N log. Yeah. So you can use that kind of approach. Can you do it in order of n time?
The order of n time is like keeping L0 as the first peak element, then from range of the list, going through the range list items,
Yeah.
from second element to penultimate element,
Yeah.
and checking out its neighbor and updating the peak element accordingly.
Exactly.
And then in the last one last if condition, checking the last element of the list and
Exactly.
updating the peak element accordingly.
Exactly. Yeah. So exactly. So we will just run through this list from starting from here up to here. Okay. Why up to here? Because we know that we have to check the neighbor, both the neighbors, right? Left neighbor and right neighbor. So if I run my algorithm on up to the last element, so my right neighbor of last element, as soon as I write something like, I mean, the let's say the index is the variable which is storing the current iteration, right? So if I write index plus 1, as soon as I will write this, and let's say index is pointing over here, I will give a array out of bound, right? So it's not, it would give me a problem. It's a compilation error. So I will be in an error. So that's why we are not going up to the last element. We would run it up to the penultimate element as told, right? And then we will simply check that when you are at 6, check whether the I minus 1 and I plus 1 conditions are holding or not, whether I mean your a of I is greater than a of I minus 1 and a of I is greater than a of I plus 1. Fine. If that is the case, you can return it directly, right? Simply return AI. That's it. And over here we will have a for loop, right? And that would run y from 0 to n minus 1. I mean, n minus 1 means here it would be n minus 2 actually, right? Inclusive n minus 2 value. So this would be the bus 3 lines algorithm code, order of n time. Right? This gives you an order of n time. So basic approach is this thing, right? But now you have to think of a better way to answer this by using divide and conquer. So how can we do that? Okay. So see, so the thing is, that's what I was telling, that you do not have to think about sortedness or anything, right? So when you think about sortedness and all those things, it would obviously take n log n time or something like that. Don't think it in terms of all those things. The idea is, here I'm only telling you to have return any element. We are not giving any other constant. Just return any element which is greater than the two neighbors, right? You have to do it in log n time. Whenever you see this expression of log n in any question, you know you have to do something so as to remove other half. I mean, any step inside your algorithm, you should be able to remove the other half of the data structure. You should not require to traverse through the other half of the data structure, right? So every time, maybe half, maybe some fraction, that you all know that in quickshot we may not be iterating every time, or sorry, dividing the list every time into half. It can be any fraction, right? It may be 1/3, 7/10, anything, whatever, doesn't matter, but it should be some rational number. Okay, and it's better if it is half, near to half. So that's the idea. You have to divide it into subparts, and one subpart you will choose intelligently such that your algorithm will work in that subpart for the next iteration, and the other subpart you will remove, you will not check. When this kind of feature is there in your algorithm, then it will give you a log n expression. because we are dividing the array by some rational number, by some fraction, right? And that's why you are getting log of that fraction as the base n. But asymptotic complexity does not consider that fraction, so it is log n. So now how can we do that? Okay, so the first thing is just randomly go to the middle element, because we know what is your idea. Okay, so this is very important. Think how to approach, because any new problem you see, you have to think about the approach. So how to approach this problem, you know, you have to take a log, you have to come up with a log n time work. You cannot do sorting or anything like that, because that takes n log n time. You cannot linearly travel, because that takes n time. So you need log n, means you have to have something such that you can ignore some part of the array. Okay, so I just randomly jump in between. Let us see what happens. Okay, so I just randomly jump in between, in the middle, right? So when you have to ignore something in binary search, what did we do? We went to the middle, right? So it's not sorted here. This is not binary search also, right? We are just jumping in an unsorted array at the middle, arbitrarily. Nice. Okay, so next thing, what we can do when I am at 4, what all the conclusion that I can draw? What I have to do is I have to check whether it is greater than left and right element. Okay, so I do that. Okay, let's say I am at one, at least I am at one element. Let's check. So I check whether it is greater than its left and right element. So I see it's not greater than the left element. Correct? It's not greater than the left element, but is it greater than the right element? Yeah, it is greater than the right element. So what does that mean? That my left element, which is greater than my current element, right? It is greater than my current element. So I can be sure of one thing. Can somebody tell me what is that one thing? And that one thing is regarding the result that I would return. What I can be surely say about the result at this point? If what result means final result, what can I say? That the result should always contain this or should never contain this. So what is that this over here that I'm talking about?
Never contain this.
Never contain this, correct? Because if my this value is smaller than my left neighbor, then what I can always say, my result would never contain 4. That is impossible, because it has violating the condition. Fine. Likewise, I can also say my result would never contain 0, because it is smaller than 4. Correct? I am saying my result will never contain, will never, under any circumstance. I have not converged the algorithm. I don't know what will happen in the future, but as of now, I can say it will never contain.
So we can remove these 2 elements.
Two. Okay, let's think about that. Will never contain 4, because it is lesser than 9, and 0, because it is greater than, I mean, the element itself is greater than 0. Fine. So my will not contain 4 and will not contain 0. Both of them would not be there in the result. That one thing I can just tell in the first iteration. Okay. Now, did we tell you to actually check for a particular number which is the greatest among, I mean, so we did not tell in the question, you have to find me the greatest among all the number which satisfy the left and right neighbor condition. So there may be multiple number which are greater than its left and right neighbor. Correct? In a list, there can be multiple such situations. Let's say 2, not say 2, let's say 10, 7, 6, and then let's say 9, okay, and 4. So 10 is also greater than 7 and 6, and 9 is also greater than 6 and 4. So 10 and 9, both of them are possible answers to the question. But we are telling you return me anything. You can either return me 10 or you can either return me 9. Fine. So if that is the scenario, when I am standing at 4 and I know my left neighbor is greater, my left neighbor is greater than 4, I can track this particular number, right? I do not have to think about anything else. I can track this number. I can go to that side and confirm it. I would come to this side later. Okay. 0 and 4, we can remove these two numbers. That is correct. But since I have got a more preferable candidate, correct? See, what I'm trying to say is the essence is in binary search, what did you do? You came to the middle. you check whether it is greater or lesser than the key value. If it is lesser, right, if the current key value is lesser, then you know that you have to move right side, because your sorry, if the current this index this value in the array, if that is lesser, then you know that your key is greater. That means your key should be there on the right hand side. Why? Because your array is sorted. So you had this conclusive argument that you have to move right side. But this, since this array is not sorted and I'm just making an arbitrary move to the center of this array, I don't have any conclusion whether I should move right or left or what should I do. Correct. So I have to have some kind of conclusion, some kind of idea which would be better, which side to move. I cannot go left and right because it's not sorted. So the idea over here is, since we are not restricting you to give me the result of the greatest among all the elements which are meeting this left and right neighbor condition, I am happy with any one result, right? So I would track the two preferable candidates that I have, whichever satisfies the condition of being greater than my current element. That is my next prospective element to be judged. Getting the idea? Because that is greater element. If that is greater element, it has a chance that it may be greater than its left neighbor as well. Because already I know when I'm comparing 4 and 9 that it is greater than my right neighbor. 9 is greater than my right neighbor, because right neighbor is myself in this iteration. I am 4 in this iteration. I can see my right neighbor 9 is greater than me. So that means when 9 is on the iteration, it would be greater than the right neighbor, which is 4. And it may be, I have to check that when I go to 9, whether it is greater than the left neighbor or not. Fine, that is the idea. So you check whether your left or right neighbor, whoever is greater. That means you are sure you are not in the answer because one of your neighbor is greater. So that may be the next prospective candidate for checking. So that's the idea. So you go to that side in order to check whether that is a valid answer or not. If not, then
no, but if we don't have to preserve the list, then why don't we remove the elements?
Exactly, we will do that, but not 0 and 4, the whole thing on the right side. We discussed now that since 9 is there as my next prospective element.
No, how can I be sure that we can delete whole thing on the right side?
You may not, you need not be sure. As of now, you are rejecting this right side. Okay, so when you actually go through quick sort,
intermediate.
Correct. When you, in binary search also, when you go, you reject one part and then you don't know what will happen, but you again go to the right
binary
side.
Search is because it is a sorted list.
Yeah, that's why.
In binary search.
It's sorted list, and you are going at one side, you know for sure that this side I would get the result, or if I do not get, then that means the element is not in the array. Correct. But you had a conclusion that I would go to left or right. Here, since what is the idea over here? Here, idea is not about sorting. Here, idea is about finding a greater element, right?
Correct.
So, since my left neighbor is greater, I am just going to that side. Okay.
As of now, at current iteration.
Current iteration. But if I find that to be the answer, what I have done actually, if I find 9 to be the correct answer, I have actually ignored this whole part of the array. Right? Effectively, not literally. Effectively, what would happen if 9 is the correct candidate? Then I can simply, I have not gone through this whole part, right? Not only 0, 4, I have not gone through, I have not iterated through 0, 4, 8, 1. My algorithm has not seen this value at all. Fine. So that is the idea. Then we will go left, and we would find what's happening. Or if, let's say, on the right hand side.
No, instead of 8, it was 18.
Instead of 8, it was 18. Okay.
Then.
Fine. I am not telling you to return 18 or 9. That's what I was telling, right? If in an array it's 7, 10, and 6, and then 9 and 4, you can either return me 9 or 10, anything. 10 is also a correct answer because it is greater than 7 and 6. 9 is also a correct answer because it is greater than 6 and 4. So you can either return me 9 or either return me 10. Here, that if you say that it is 18, 18 is also a correct answer, 9 is also a correct answer. I'm not worried about that. Because 9 is greater than its left and right neighbor, 18 is also greater than its left and right neighbor. Only thing is I need a number which is greater than its left and right neighbor, and you should give that in a log n time. I'm not telling you to give me a number which is greater among 9 and 18. Okay, so that's the thing I was telling at first. That's why I gave this example. Fine. I'm just telling you, give me one number. there are multiple answers to this. I just want any one number which satisfies this condition in a log n time. Fine. That's why I can have this liberty, and that's why that is the point that I cleared at first. If I would have told you that you first find all the numbers, put them in a list which has its left and right neighbor smaller than itself. So let's say there are 5, 6 such numbers, right? And then you give me the number which is greatest, right? The maximum number. So then that would have to be dealt in a separate manner. But that's something that we are not telling here. We are telling you just give me any number, but the time should be log n. Okay, and conditions should hold. So 9 you can return, 18 also you can return. 18 only reason I'm not going to 18 because I have to write an algorithm that would work, right? So now since I'm on the 4 value, I'm just checking 4's left and right neighbor. That's it. And I would go to the side where I can find the greater value. Okay. So if I would have landed at 0, I would have landed at 0. Let's say reduce one element over here. In this example, let's say I did land at the 0 value, right? Let's delete all this. Okay. So let's say I landed at 0. 1 was here. So now I would see 4 and 18. That whether 0 is greater than 4, no, it is greater than 18, yes. Now since it is greater than 18, 0 is greater than 4, no, 0 is greater than 18, no. So 0 is an element which is smaller than both its neighbors, so it's never the answer. Fine. So then I can compare that whether the left side is more, whether the right side is more. Whichever is more, I can go to that side. Okay. The main idea is I want to go to an element which is greater. That's the only idea. Fine. Okay, so let's continue that. We were at 4 and there was an element 2 over here. Fine. 4. So I go to the left side because 9 is greater. So I go to the left side. And again, I see since I now what is the subpart of my array that I'm checking? It is from 4 to this part. I mean, this part. This part of the array I'm now checking. Okay, so I go to 9 and see whether it's left and right are holding the condition or not. So I see, yeah, 9 is greater than 6 and 9 is also greater than 4. So I simply return 9. Okay, so that's the idea. But obviously, I have to also think in terms of the other way, right? So what happens? This was the case where my left neighbor is more. This was my first element and my left neighbor is greater. What happens if my right neighbor is greater? So let's say this was 10. Fine. And let's say this was something like 1. So accordingly, I have to think about that I would go to the right side. This part of the array I would consider. So both the recursive call, you can understand that I would go to a subpart either left side or right side, depending upon my neighbors. If I see the neighbor to be greater, then I go to that side. That's the only idea. Fine. Now, so that's done. But what would be the next case? I mean, once I go to the left side or once I go to the right side, whichever side I go, I should check, right, whether my left and right neighbor is greater or, I mean, lesser than my current value or not. So that is the one check that I have to do. Bas, that's it. 2 recursive call and 1 base case where you check whether your left and right neighbor are smaller than you or not. So now we will write the code, and while writing, we would find one corner case that would come, and that we would discuss. Corner cases when we reach the end, as in the previous example also, when we discussed it using the order n time approach, when we used to travel till the penultimate element, right? As you told. So as Mr. Binglish told, so we would go to penultimate element. But here we did not do something like that. We did not discuss. So what would happen when I reach over here, right? Just a second. What would happen when I reach at this element or at this element? What would my algorithm do? Because now it does not have its left neighbor and here it does not have its right neighbor. Okay, so then we have to check for this element, we have to check whether it is greater than its right neighbor, and for the right element we have to check whether it is greater than its left neighbor. Right? That's already mentioned in the question. So this feature, when there is only a single element, depending upon which side it is, you only check one of the neighbors. So that condition we have not yet discussed, that we would discuss in the code. Just one small condition we would have. Fine. So let's write the code as of now. Okay, so let me just read it once. Function find peak, right? Find peak. It's small. Find peak. Okay. Okay, so obviously I have to, since you know that we discussed the approach, we would go left side, right side. So it would take the, I mean, the low, high, all those parameters, right? The array, the low index and the high index. And since it would be recursive, obviously I would need the ln, the left and, sorry, the low and high, the lower and upper indices. So that I have to pass recursively in the find peak method. So, but if you see in this question, it's told that find peak function definition has already been given. Find peak, and you are only allowed to pass the array itself, right? Nothing else. So basically we would need another method to do all our tasks. Here we will only just get the array and pass it to the other method. That would actually be working. Okay, so let's do that. I could have just changed over here, but in exam or anywhere else, if you see a specific definition of a function given and your approach to solve the problem requires a separate function which needs other parameters, right? So, and this suffix code would be fixed, you cannot edit it. So in that case, better to just define the function they have given and simply pass it to another function where you can write your approach in your own way. Okay, so I would just do that. So let's take an element, say size equal to, okay, I need the size, and then let's say, okay, I have to also call another method. Let's call it utility. Okay, and in this I would pass the my required parameter. Lower would be 0, and lower index, and the upper index would be size minus 1. Fine. Okay. Let's call the size also. Fine. Okay. What is the error? Oh, utility is not. Okay, so let's define our what is this? Expected. Okay. Fine. So at first we jump to the middle, right? So we have to, oh, one more thing. This is returning, right? Okay. Yeah. So we jump to the middle, right? So we have to first find the middle. So that is simply high minus low, right? And so mid is done. After that, I have to just get the element. What is that element? Let me store it in that only. Okay. Okay, so now let's do the recursive part first, and then we would go to that checking whether the left and right are equal or not. So recursive part, what was the idea? That if whichever side neighbor is greater, I would go to that side, right? And one more thing, obviously, when I have to work with this mid, I mean this mid value, right? So I must check whether the I mean whether the index, that is the mid value, is within the array or not, because I'm dividing every time by 2 by 2. it may be the scenario when it has been 0, right? It has become 0. So if it has become 0, then that is the edge case. So I have to consider my normal cases when it is greater than 0, the normal within bound check, right? So I would just do that. So what to do? So if I write if my mid is greater than 0, and now the condition. So let's take the first case where I would go to the left hand side. Okay, when I would go to the left hand side, that means my left neighbor was greater. So mid minus 1 uh, is strictly greater than my current element, right? So it is my greater than my mid, right? So if this is the case where I would go to the left side, because mid minus 1, the left element is greater. So I just recursively call the utility method only on the left subpart. Low, high, size. So low would be low. Okay. And high would be on the middle. I mean, the mid would move, right? Mid would move to the left hand side. Sorry, the upper would move to the left side. That is towards the mid. So I would write mid, and obviously the edge element I would not consider. So mid minus 1. Okay. And the size itself. So that is what n, right? N. Actually, it was not required anyways. I thought it would be required. Fine. Yeah. So this is my one recursive call. Obviously, the other would be on the just similar on the right side. If mid greater than 0 and mid plus 1, that is the right element is greater than L mid. In that case, I would go to the right part of the array, and that should be my lower would be mid plus 1 and upper would be as it is. Fine. Okay. So now comes the main part where I have to check these recursive calls are done. So I have to actually now check whether it is greater or lesser, that part. And since I'm writing if, it should be actually elif. Okay. So what are the things that I have to check? Simple thing, that is my mid, if that is greater than my mid minus 1, and my mid is also greater than mid plus 1, right? So if that is the scenario, you simply return mid. Okay. Okay, so that's it. And now let's see whether this code would work or not. Okay. So see, just that simple thing. I'm just checking whether my middle element is greater than the left neighbor or right neighbor. If it is so, because now this is the base case, right? This is the return case. In any recursive algorithm, the way you do the base case, this is that case. And all the other case over here is the recursive case, these two, that whether I should go to the left side or right side. Now you can see, so if I apply, let's take any of the test cases over here. Okay, it's very, very big. Okay, fine. So let's take this test case 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2. Okay, so this test case, what would happen? So I am jumping in the middle element. Okay, I don't know. Let's say, let's consider, for example, this is the middle element. Fine, 9 is the middle element. Okay, so now you see that whether I mean whether 9 is greater than the left side or right side, both side or not. actually it is greater than both the left and right side. So in the first iteration itself, it can give me the correct result, which is 9. Fine. So it's not a proper way to judge. Let's take any other example. Okay, this is fine. So let's say I would jump in the middle at 5 in this question. 3, 4, 5. Okay, at 6 most probably. I would jump at 6 in the middle. So if that is the case, if I'm jumping at 6, I see that 6 is greater than 5, but it's not greater than the right neighbor, which is 7. Correct? So 7 is a number which may be a prospective answer to this question, because 7 is greater than 6. So 6 is at least not the answer. Right? So I would jump to the right hand side. Okay, when I'm jumping, I'm not telling that left hand side would not have an answer. I am never telling that. Left hand side may also have an answer, but we just want one answer, which should be greater than its left and right neighbor, and you should be doing that in a log n time. That's right.
So basically, question is asking return at the first occurrence of any such element.
Exactly. But now it depends on your code, which one is the first occurrence. If you do a linear scan, your first occurrence would be on the left side some element, right? So let's say in this case, this example, that would not work, but this case, both left and right element would be 8 only. If you do a linear scan and if you start from middle, in both case 8 would be the answer, because there is only one element which is greater. But let's say I have, in place of this 2, 5 is there, right? So let's say 5 was there in place of 2 and everything else is same. So in that case, what would happen? If you do a linear scan, your code would return 5 as the answer, right? That is this 5 as the answer. Let's assume in place of 2, 5 was. But my code, when I am going to the middle and proceeding by this approach, 8 would be returned as the answer. So which is the first occurrence, that depends on your code. So if I go in this log n approach, 8 would be the first occurrence where left and right neighbor are small. Assuming in this place of 2, 5 was there, in the 5 would have been there, right? In that test case, if you do a linear code, then obviously 5 would be returned, because 5 is greater than 1 and 5 is greater than 3, right? So that's the idea. But you have to return any one of them, it should be log n time. So okay, so let's come back. So when I'm going towards 7, right, 7 is greater than 6, so I go right side. When I'm going towards 7, I'm never saying that on the left side there would be no possible answers. Left side possible answers may be there. I am just trying any one, and that's why I'm going for 7, because 7 is a greater value and it has a higher chance of being the candidate. Okay, so I go to 7, I see that whether 7 is greater than 6, that I already know 7 is greater, and that's why I chose right direction. But I have to check whether 7 is greater than 8 also or not. I mean, it's right, which I see it's not correct, right? So now again I see, because it's not correct, that means the right neighbor of 7 is greater, which is 8. So I again just repeat my same approach and again follow the greater value, which is towards right side. Okay, so now the next thing I check, okay, 7 is the answer. Got the idea? So, and let's say if I would not have got any result, right? If I would not have, let's say on the right hand side, there would not have been any proper value. So since this is recursion, we would actually return back, right? And then when we track back, then we would actually get the answer if it is there on the other side. So that's the idea. Fine. So yeah, but one thing, I think our test cases missed that, but let me just discuss that. I was thinking at least one test case would fail. Okay, fine. We would have to introduce a new test case. See, the idea is, in this scenario, we did not consider the instance when the left or the rightmost element is the answer. Did we do that? We did not do that, right? Because let's say if the left or the rightmost element would have been the answer, so in case if the leftmost element would have been the answer, right? So this mid minus 1 would give me a problem. So in none of the test case, actually we had that kind of situation.
So suppose there is a list which is decreasing from the start and then increasing from the middle.
Yeah, that's what I'm trying to do. So let's say
No, it is passed as a list only
Yeah, yeah.
in other test cases.
Yeah, you're saying something?
No, yes, it was passed as a list. That was what I am saying.
Past. Oh, acha, this one. Okay, acha. Okay, so 6, right? Is my answer. Fine, let's check. Right. So if I see the expected output, yeah, it would not work. Yeah. See why? Because we are actually running into a problem. We are running into an error because of that -1. So this case, or let's say this is 6, 1, 2, 3, 4, right? Or let's say in another case it would have been 1, 2, 3, 4. Yeah. So actually in this 1, 2, 3, 4, if I give, then also it could work. If I give 1, 2, 3, 4 only, then also the answer should have been only 4, right? Because it is greater than its left neighbor. So okay, so in 6, 1, 2, 3, 4, the 6 is the answer. In 1, 2, 3, 4, 4 should have been the answer. But we so basically in the leftmost or rightmost element, we have to just modify. We have to do something. We have to think about some condition. Now, what is that condition? So what is happening over here? Let's see that. Let's analyze that. So we are actually moving one by one. If the left side element of my current element is greater, I am moving towards the left side, or I am moving towards the right side. Correct. And then I'm just considering that part of that subpart of the list. So again, I'm finding the middle of that subpart and proceeding. Okay, so I'm just every time I'm finding the middle and then I'm proceeding. So obviously here I have to add one condition, whether my middle is the first element or not. Middle is equal to 0. Okay, now you see, let me just tell this. So when are we going towards the left side? So if I come over here in this example, okay, just a second. Right. So this was 1. Okay, so oh no, it's not 10, right? It's 0. Okay, so when were we actually moving towards the left side? So I was at 4, then I moved towards the left side. According to the code, I go towards the left side. Now what would the code do? Let's go to the code. The code would again calculate the middle, right, at line number 3 on the left subpart, and it would go to the middle element, and then it would resume its task. So let's go. So in this part of the array, I would directly not go to 9 according to the code. I am going to the 6 again, right? The middle element of 2, 6, 9. And then I am checking whether 2 is greater or 9 is greater. If it is not, then I am again calling, I'm just proceeding, right? So what would happen in the next iteration? I would come to the middle 6. Then I would check the left side and the right side. And I see that left side it is smaller. 6 is greater than the left side, but 6 is lesser than the right side, right? So I would again call my next recursive call by moving towards the right part. So what is the current situation now? This is the subpart of the array on which I am iterating in the next part after 6. So after 6, I am iterating on this part of the array, but it is a single element. Correct? It's a single element now. And that's why it should be the answer. Okay. So how to actually check that? When would this happen? I'm just checking the left and right neighbor, that is fine. But let's say when I traverse in this way and my single element, this last element, the single element that I'm talking about, right, in the subpart of the array is the leftmost or the rightmost element. So in that array which we just had 6, 1, 2, 3, 4, right? I would come to 2 at first, right? And then I would not get. Then again I would check which one is greater, right? I have to move either right or left, but I see that right is greater, so I can go to the right side, right, towards 3. And if I go towards 3, so then what would happen? See, then also would I get the correct result? No, because 3 is lesser than 4. So I would not get 3 as the correct result. Then again I would move towards 4. Now if I go to 4, okay, so one little mistake I made in the test case, the answer should have been 4. But anyways, so when I go towards the right side, again at 4, now I must check. Now this is only the sub part and this is a single element. I have to check whether the left side element is smaller than 4 or not. Okay, so I must have some condition like this where mid is equal to n minus, okay, so what was the length? Anyways, n, right, n minus 1. When this is the case, correct? And what I can say is the left element, right, the mid, I mean your left hand side element which you are considering, that is actually lesser or not, correct? That I have to consider. But one important issue is that I was telling about is when you are going towards the right, right, in the 3th recursive call, when I'm calling the recursive call on 3, what I am actually checking is whether when I go towards 4, the left element should be smaller, because in the next iteration left element would be 3. So that condition I have to add, and accordingly when I'm in the first element, the right element should be smaller. That condition I also have to add. So I would just add that condition and you would see that how it's working, right? If my middle element, if my mid is equal to 0, in that case, or let me just write it and then I would explain what has been done, right? Or my L mid element is greater than the mid minus 1 element, right? Yeah. If my middle element is, then middle element would be greater. Yeah. Just add this. So here it would be just the other way around. It is the last case when my L of n minus 1, sorry, L mid is equal to the last value, or my
L mid or only mid?
which one? Oh, sorry, mid. Just comparing that. My mid is greater, I mean equal to n minus 1, or L mid is greater than this value. Yeah. Fine. This should be 4, right? Right. Yeah, that's what I was telling you. This should be 4 because I'm going towards the right side. See, again, let's just repeat that thing. That I thought that 6 because we are adding 6, but ultimately the algorithm proceeds towards the element which is greater, right? Any of the direction which is greater. So 6 is also an answer in this case, and 4 is also an answer in this case. But since I started my algo from 2, right? Since I started my algo from 2, so I jumped towards the element which is greater neighbor, which is 3 in this case. So that's why I am going towards the right side and I end up with the answer 4. The correct answer is 4. But let's say if you do a linear algorithm, that we just discussed in the first scenario, right? Order n time. So that would give you 6 as the result because 6 is greater than 1. Right. So which one is your first occur element that your algorithm, experiences? That depends on the way you are writing the algorithm, but any of them would work as long as it's log n time. That's right. Fine. So you can see the algorithm here, it's returning 4, and 4 is actually the correct result because we are going towards the right side. But what's important is until and unless we write this mid equal to 0 and n-1 condition, 4 was not coming in the answer, right? 4 was not coming in the answer. It was coming as a blank. I mean, nothing was coming, right? If I would not have written this mid equal to 0, mid equal to n-1 condition. So these two conditions we have added. Fine. So see, the idea behind this is you have to spot which part of the code is necessary for you to work and which is not. If you can decide that, then you would be able to visualize an algorithm. So in this case, which was not necessary part was that you did not have to have a sorted list. And second thing is you did not return the result which is greatest. I am okay with any of the answer where if it is greater than its left and right hand. So when you have these less restriction, that is the thing that we have to exploit in order to make your code, in order to use the divide and conquer algorithm. Okay, so the best way to think of divide and conquer is what are all the restriction what are the freeness that you have, that is you do not have those restrictions, right? You can just think of that. Sorting is not required. Any of the answers you can return. Okay. So now you just jump into the middle and find arbitrarily. Okay, because any of the answer would work. Fine. So that is the idea. So spotting these kind of things is very necessary. Let's say in heap we discussed, right? So whenever you see you need to extract the minimum or a maximum value from a group of data, and also that group of data is not constant. You are continuously adding element into that group of data. And again, maybe in the process you are again extracting minimum or maximum element from that group of data. Whenever any algorithm uses this approach, you need to have heap in the algorithm, right? Whenever you are extracting only the minimum or maximum data but not modifying that data set, then you can simply do it with a sorted array. Okay, so these are the ideas. I mean, where you can spot which approach to go. Fine. So this was one question.
Suppose we need to find out the biggest such element.
So then you have to think of another way. If you have to find the biggest such element, then the first thing is you cannot do divide and conquer in this way, because you have to have all the elements which satisfy this condition. Correct. I mean, you cannot just ignore the others. So in this case, I should have 6 and 4 both in the set, and then I have to compare which is greater. So if you just add that constant, I think there is no solution other than order of n, right? Order of n is the best way. Okay. Yeah. I don't think, because anyway you cannot divide and conquer's basic idea is you have to ignore a part, right? That's the main thing that I'm trying to communicate. Divide and conquer would only give you result, proper result, when you are able to ignore a part of your array. Like in quick short, why quick short was giving order n squared time? When although you are using divide and conquer, right? Quick short we are using divide and conquer, but we are not getting order n log n in all the scenarios. In the worst case it is order n square. Why that is the case? Because although you are using divide and conquer, but essentially you are not able to ignore a part of the array when your pivot element is actually the last element or the first element, right? You are not able to ignore a part of the array. Every time you are choosing the pivot, it is actually the first or the last element. So your array size is decreasing by 1 by 1 minus 1 minus 1. So it's just like linear, right? And that linear is iterated for n times. That's why it is n squared time. So that's the idea. Divide and conquer would give you result when you are able to work in a way such that it ignores a part of the array. That's the main thing that you have to think of. So whenever you see a problem asking you to have a log n time complexity something, or maybe divide and conquer anything, right, related to log n or divide and conquer, you must think of that I have to eliminate a part of the array somehow. Now in order to judge that which part to eliminate, you have to think about what are the freeness that I have, what are the less restriction that is not imposed on me, and depending upon those restriction you have to think of the algorithm. So this is how you approach a problem when you see a new problem, right? Fine. Okay, fine. So basically this comes with practice. The more you do multiple questions, I mean, none of us can do that in just by seeing problems. It comes with practice. When you see more problems, you would be able to find out.
Yes, in this utility function, we can remove parameter n and simply pass that as a length L.
I thought that okay, it would require me, but L
I
is
did
not.
that, it passed.
That is not required. Fine. Okay. Yeah. So am I missing any condition? Left is done, right is done, middle is one, and either I'm going left or right. If I, yeah, then also it would. Okay, fine. I don't think I'm missing anything. Yeah, so it's okay. Yeah, fine. So let me publish the other question. Fine. I have published the second and third problem is for you to try, because I would discuss the fifth problem, which would actually be kind of a superset of the third problem. Right. So third problem I will not discuss. Fifth problem I would discuss at the end. And fifth problem is something which is actually the kth smallest neighbor. It's not neighbor, kth smallest number, which has been explained in the slide as well. So we would do the coding for that. So that would also clear a lot of your doubt about median of median, the fast select, all those things. Basically the lecture 5 and 6. So I have,
Yet to cover those lectures.
yeah, fine, no issues. I would try to discuss it in a grounds up manner, but yeah, after that, please check the lectures. Or maybe after checking the lecture, please revisit this, hopefully. Lecture 5, I would, sorry, problem 5, I would try to discuss directly in a grounds up manner. So I hope it wouldn't be a problem.
Sure.
Okay. Yeah, so problem 2 and problem 5 I have published. You may try problem 2. Okay, so at least think of an approach how to solve that. The approach is important. Coding, I mean, it would come with time, but the approach to how to approach a problem, that is the main intention of this course. Yeah.
In the problem, it is given that both the lists are of same size. In problem 2.
Yeah, both the lists are of same size.
Then the merged list will always be even length. Hi, Bimlesh here. Okay, okay.
So just let me give you a hint about it. This question has a very intuitive approach. I mean, just a very intuitive approach is there to solve it. Okay, I mean, just think of the values. I mean, if you have, let's say, a 6 or 8 or 7, any length array, two arrays, which are sorted, and the since it is sorted, you can assume that the middle element itself would be the, I mean, may not be the median, but it is nearest to the median, right? It can be a median if it is sorted array, middle element, or if it is a even number, total even number of elements are there, then it would be the average of the two middle elements. So basically what I want to say is when you have a sorted array, the middle element is it's kind of the median, or maybe the median, or maybe very near to the median value. Correct. So yeah, now you have to merge these two list or arrays, whatever, and that means since it is sorted, you already have the, I mean, you can tell what would be the median for these two arrays, right? So let's say for the in the example which is there, the sample input 1, 3, 5, and 7, 2, 4, 5, and 8. These two are the arrays. So since this is an even number array, right? The total number of elements are even. The median of the first one would be 5 plus 3 by 2, and the median of the second one would be 5 plus 4 by 2. Okay, so yeah, so that is the case. Now, what you can infer from the values of these two medians. So in the first array it would be 4, and in the second array it would be 4.5. So 4.5 is greater than 4. So what does that tell you about the array B as compared to the array A? So comparing the median of the two arrays, what can you infer? Okay, so that is the core of this algorithm. You do not have to merge these things. You are not joining them or anything. You just are making an important, intelligent assumption, not assumption, sorry, intelligent conclusion, and that's on the
Yeah,
basis of the
I thought that these two are sorted lists.
yeah.
So we'll find a median for both the lists separately,
Yeah.
and whichever median is higher will return that.
No. If your median is higher, no, I did not get. You find the median separately, then
Then anyway in this merged list, that median will be either of the two.
yeah. So in the first list 1, 3, 5, 7, the sample input, right? In that the median is 5 plus 3 by 2 because it is a even length list.
Yes, so it is 4 in the first list and 4.5
Yeah.
in the second list.
Yeah.
So 4.5 being higher, we will return that.
Okay. 4. You said the 4.5 being higher, you are returning that, but 4.5 is not the median, right? It may not be the median. 4.5 is the median of 2458. But when you join these two lists and then arrange them in an ascending order, right? So when I join these two lists, what would be the result? 1, 2, 3, 4, 5, 5, 7, 8. If I join these two lists together, 1, 2, 3, 4, 5, 5, 7, 8 would be the ascending order of that merged list. Then if I calculate the median of that, right?
In this particular case, it is coming 4.5 because the
Acha, here it is
middle
coming,
value
right?
will be 4.5. Yes.
Okay, no.
Generalize.
Yeah. So here it is coming 4.5, but let's take the other example. So over here, what's happening? If I do it, here the median is what? 3 plus 4, 4 plus 3, right? 7, 3.5. And here it is 9 plus 10, 18 by 2, that is 9.9, right? Yeah, see here it was 3.5. Here it is.
And here also middle element will be 6 and 7.
Which one?
In the merged list, it will be 6 and 7. Okay.
Yeah, I mean that you in this case also see after 6, 7 is there. It's a linear list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's why it is happening. Here it was happening just randomly. I mean, it was coming 4.5 and that's why it's happening like that. But here it is happening because it's a linear order broken up into two lists. That's why you can see that 6 and 7 by 2. But here it is 6 and 7 by 2. And here the approach was different, right? You said that you find the median separately for both the list and then you return the higher one. But if you do that in this list, it would not work. So it would be 3.5 in this case, and it would be 19. That is how much? 89.5. 9.5. 9.5. So 9.5 is not the answer. That would never work because see, what is median? You are joining all the elements together in the list. I mean, in a merged list. When you add all the elements of both these lists together in a single list, and then you are sorting that list at first, right? And then the middle element is your median. So I cannot tell anything from that perspective. What might be a better approach is the median of median, which I don't know whether you have seen that or not. Median of median concept, which is you find the median of the first list correct. Second list also you find the median, that is also correct. And then you find the median of that value, not the greater value. Okay, so I get the result in this case, let's say what was 3.5, right? 3.5 and 8.5,
9.5.
9.5.
9. Yes.
So 10, 11, 12, 13. Correct. 13, sum the both the median, sum both the median, right? I want to find the median of those two median. So since there are only two numbers, how can you find the median of two numbers? A plus b by 2. Correct.
Correct.
So in that case, what is happening? See, I got 13. 3 plus 4 is 3.5, and here it is 9.5. So 9.5 plus 3.5, that is the sum of both the medians. I'm getting 13. And I find the median of these two median, which is basically 13 by 2, that is 6.5. Okay, so I don't return the higher median, rather I try to find the median of median of median. I continue this process as long as I have. So here we have only two lists, but let's say there are 4, 5, 8, 9, whatever, 10 lists would have been there in that. I mean, in this question, we are only working with two lists, but in a general case, if there are multiple lists, you find the median of all those lists, right? And then you find again the median of all those medians that you founded for the each list, and continue the process until you reach to a specific value. Okay, so that is actually, but one important observation is that might not always be the correct answer. But one thing is sure, that would be very much closer to the correct answer. Okay, now when you see the lecture that sir has given on median of median, you would see why it may not be always the correct answer. But one thing is for sure, it would be a very, I should say, a very close approximation of the correct answer. So here it directly matched. I mean, 13 by 2, we got 6.5, but it is also not the exact correct answer. Fine. I mean, this approach would not always give the exact correct answer, but this approach would at least give you a very proper, very close approximation of the correct median. Fine. So if you say that I would have an approach like this, approximation approach, that should not be the maximum of the median that you are getting of each list. You can tell that I would find the median of all the medians and then I would give the result. That would be a better approximation. Fine. But here we are not going for approximation. We need the exact answer. So let's discuss how to do that. Okay. So see, let me just tell one thing. So let's say I have an array. Okay, and I'm purposefully not writing numbers, rather I am representing it with some graphical, I mean, drawing kind of way. So let's say I have array A, which is in an increasing order, right? It's sorted. So I'm just, these are the circles which represent the magnitude of the numbers. Okay, so this is my first array or list, and my second array or list is also there. Let's delete a few. And one more thing, I'm trying to make these circles in a way, and you should think of this circle. I mean, you should compare the sizes, right? When I'm drawing this, try to compare the sizes. So right, 5 elements in each array. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Yeah. Yeah. So these are the two arrays that I'm talking about. Okay, fine. Now see, the idea is my median would be at the middle, right? Because it is sorted. So the median of array would be at the middle. Correct. So obviously I can assume that median would be, since how many elements are there? 5 elements are there. Right? Let's draw one more element. With even number, it would be more difficult. So let's consider that case. Okay. So my median would be where? It would be something, the average between these two numbers, right? Sorry, not numbers, these two circles. The average of these two circles would be the median of A. And in this case, in case of B, what would be the average? The average of, I mean, the median of B would be the average of these two circles. But what is the observation that we can do from here by comparing the median? What is the observation? Observation by comparing median of A and median of B. Now, since A and B are sorted in this case, I can directly write okay, and this is, let's say, comparing approximation, not exact median, comparing approximate value. Okay, I'm not exactly going for, I mean, that's what I was saying, that I'm not judging the exact median. What I'm judging is the A mid and B mid. Okay, but since this is sorted, it would be a near approximation of the median. So what is the idea that I can get? See, I'm just telling one thing, and then you ask the doubts and the counter arguments. The idea is, let's say, what is the final thing that I have to make? I have to make a list C that would be A plus B, right? That would have all the elements of, actually not A plus B, A union B. Plus is kind of concatenation. I'm not concatenating, I'm making a union. That is, it should have all the elements of A and B, and it should be, I have to find the median of C. Median of C is something that I want. Fine. Now, I'm telling you, I will not be joining the list A and B. I'm not joining list A with list B. And I mean, basically, I'm not going for the merge algorithm. So if I just tell you what would be the first approach to solve this problem, you would say, okay, A and B are already sorted. Fine. We know how to add, I mean, converge two lists which are sorted, right? That is essentially your merge algorithm of merge sort. So you simply do merge algorithm, which gives you order of n time. Correct. And once you do the merge algorithm, you would get the C array, which is already in a sorted order, because merge algorithm creates the sorted array. And you simply say the middle element, right? Now middle can be middle, or I mean middle plus one, that average kind of thing. If the condition was given, if C is even, then it would be the middle by 2 and middle plus 1 by, I'm sorry, middle plus 1 by 2, that thing. Or if it is odd, then it would be directly the middle element. Fine. So you can directly answer that. That would take your order of one time, not order of middle. Sorry. I mean, that would take you order of one time, and your merge algorithm would take you order of n time. But that solution takes order n time. But I need an answer in order log n time. So I cannot join it. That's the first restriction. I cannot converge these two array into a single array, because that would take me n time by using merge algorithm. And if I randomly join them and then sort it, then it would take n log n time. Fine. Okay. So what should we do? So what we do is we make an intelligent assumption, not assumption, intelligent observation. And that is, I compare the middle element of these two sorted arrays A and B. Fine. And then what would I have to do? I have to make all this element, put all the elements of A and B together into C, and then find the median. Correct. Now, if you see, let's say the value corresponding to this is, let's say 6.5, and the value corresponding to the median value, or whatever you say, that close to median value, is over here. Since these circles are much greater in size, so it is something around, say, let's say 10, right? That's why I drew this in the form of circles, because yeah, so just to represent this behavior, that median of B is 10 because the circles in B are bigger, and median of A is 6.5 with 5 elements only because the circles are kind of smaller. So kind of this is the value. Now, if I get this thing in my ultimate list C, what would happen? What would be the median? What would be the middle position of the C list? What should be the value? Can I guess some value? It should, whether it should be 6.5 plus something, 10 minus something, maybe the average. How should we do that? What can we do that? See, how can we do that?
It will be of last two elements in A and first two elements in
exactly.
B.
Exactly. But only thing is, it would not be last two or first two. We have to understand it in the form of first half or last half. Here I'm taking a fixed example. I mean, I have taken 6 elements. So, and the median is calculated by the middle two, and that's why you are calling the last two and first two ID. But when it is a in length list, we have to just do it. What, upper and middle? I would just shift my upper over here and calculate from up to this part, and I would shift the lower in case of A over here. This would be my high value, and this would be my low value. So just same thing, correct? Exactly, great observation. So that's what I was trying to say. Whenever you are merging all these elements and putting them into a list, what I can tell about the median of that list? I'm not merging it. I'm just thinking of merging it. I can, that's the observation, that it would be a value which would be middle of the first right hand side and the other one's left hand side, something like that. Okay. So whenever you see the median or the middle value of A or B, I mean, in this case, I mean, either one of them, let's say B is greater. So in that case, you change the upper lower accordingly towards the left of B. And because you want to reduce, since B's median value is more, so, you know, in case of C, when I put all the element, I would go towards the lesser side of B. And since A's median value is less, when I put all the element, what would happen? I would move right side of A, greater side of A, right? So that's the idea. So accordingly, you just move these halves, you go to the right side or left side. And also,
so we are comparing the median of two lists,
exactly.
And whichever is having a lower median, we are going to the second half, and whichever is having the higher median, we are going towards the first half.
Exactly. And why we are doing so, you made the observation. So I understand you already have got the idea. Intuition is because that's why I kind of tried. I don't know how much justice I did with it, but that's why the pictorial representation, that is, these circles are smaller in size, sorry, bigger in size, and this, I mean, in this case, these circles are bigger comparing to, okay, let me just state it. These two circles are a bit bigger circles, right? But in A, the average size of circles are smaller. In case of B, the average size of circles are greater, and that's why you got a greater value of the median in case of B, right? And that's why in C, when I put all the elements together, what would happen? The median would be in the middle, right? It would be the middle element. So if it is in the middle element and it has all the elements of A and B, the intuition is I must move towards the left side of B because B's median itself is more. So in C, when I put all the elements of A would come, and the average of that would kind of go, median and average are the separate thing, but I'm just telling that the median of the whole distribution would move towards the left hand side corresponding to B because A is smaller. Initially, I only had B, which are very big values. And in terms of A, it would move towards right hand side. And the reason for that is now I am incorporating B along with A, where B has very large values, right? So that's the intuition behind it. That, yeah. And why median? I mean, we do not have we are not directly calculating the median, because in case of even number of element, median would be that sum by 2 value. Even comparing mid would work, because see, in this process, in this intuition, right, we are not actually I mean, it's an intuitive approach. We are not actually going into the value and checking which is greater or lesser, right? We are just on the basis of the median, this middle value, this value, right? These two value, we are deciding whether to move right side of A or left side of A. Accordingly, whether to move right side of B or left side of B. In order to make that decision, we are not making it so much quantitative that we are exactly comparing the median of A and median of B. You can do that if you want, no problem in that. We would write the code by simply using A mid and B mid. That should work also, right? Because it's sorted array. So I mean, it should be middle or maybe the average of the middle and the middle plus one element. So this is a proper approximation of the median value. That's why I wrote similar to, not equal to. Fine. So yeah, that is the idea. Now let's write the code. But obviously you would understand that I can have the recursive call like this. I can go towards the right side, and in case of B, I can go towards the left side. And that's how I can get, I am getting the divide and conquer. I'm dividing, right? This part I'm dividing, and over here, this part I'm dividing. So I'm getting the divide and conquer essence, but there should be a base case. Whenever I'm recursing using divide and conquer approach, There should be a base case where it should give the definite answer. What should be the base case? Very simple. Every time if I'm dividing the array in subparts, I would reach a point when I would end up with both size of A equal to 1 and size of B equal to 1. Right? And that would be somewhere, I mean, over here, maybe it's not correct to mark it, but anyways, it would be somewhere towards the right of A and towards the left of B. And what I can do is then I can simply average them out. Right? So let's say XA was the element of A, which is the last element, and XB was the last element of B. So at the end, if I check if the size of A is equal to 1, right? Equal to size of B, right? In that case, I do XA plus XB by 2. This is your answer. Fine. This is the base case. Now, obviously, you would understand again. Here it is A1 and B1. I have reached at that place, right? Both of them are of equal size and one size. Sorry, both of them are anyway equal size. I mean, both of them are of size 1. But let's say I can get into a situation when dividing into this subpart, I may get into a situation where size is 2, because depending upon the initial array was of even length or of odd length, right? Even if it is of even length and every time I'm dividing into half, right? And then I would obviously reach at a point of 1. But if it's of odd length, I may reach at 2 at some point, right? So those things are there. So there can be two possible base cases. One possible base case is that when the array size is 1, another possible base case can be when the array size is 2. Okay. So I'm just discussing this, but I'm telling you, if you are not initially, if you are kind of thinking this approach on your own, this A equal to 2 base case idea does not pop into your mind. Don't worry, because it never popped into our mind or anyone else's mind as well. These things come, this basic approach of solving the problem is important. Then you have to fine tune the corner cases in any approach, right? So just when you practice along with it and observe the output, you would understand, okay, so this is happening, this is a corner case. So then you incorporate a proper condition for it. So this A equal to 2, I'm just discussing because this is the scenario, but this is a corner case, and don't expect that you would understand it in the first way when you are trying to approach that problem. This would come up I mean, iteratively, but this is the basic idea. This is the basic core part of the idea, that this discussion, and then this is the base case, that when the size is 1, you return the average of it. Now let's see, while we are discussing, when the size is 2, right, when both the array size are 2, A is also size 2 and B is also size 2, when we have reached at that point, right, then also we can calculate the median. That also would give us the result directly without going into the next iteration of this A equal to 1. So how can we do that? So let me just state it. I have, let's say, inside A, 2 elements, XA1 and XA2. Fine. And in case of B, I again have 2 elements, XB1 and XB2. Just think of this expression, huh? Since I want to have C where all this XA1, XA2, XB1, XB2 would be there, may not be in this order. This may not be sorted, right? This may not be sorted. So it may not be in this order, but basically these 4 elements would be there in C. So what would happen if I write something like this? If I say that I would write that the maximum, okay, the maximum element of XA1, fine, and among XA1 and my XB1, and the minimum element among XA2 and XB2, right? If I find the average of them, so what's happening, what I'm doing, this is the scenario, huh? Please consider this part. When the size is 2, both A and B sizes are 2. Fine. What's happening over here? What I'm doing, I am finding the maximum of the least element, right, and the minimum of the greatest element. So what I'm doing, see, what I'm trying to do is, let's say I mean this XA1, XB1 were the, I mean XB1 is greater than XB2, sorry, XB1 is smaller than XB2, correct? So I can guarantee that XB1 would come before XB2 in the result set, right? And similarly, XA2 would come after XA1 in the result set, like in this case. Fine. So what I can say is, when I would arrange the number XB1, A1, A2, B2, whatever, right? So these four values would be there, these four numbers would be there, and the
So
median would be
these two relative positions will maintain.
exactly relative weight, position. Yeah, what I mean is the maximum of the smaller two values. When you take that maximum, the smaller values would be in the first part of the array over here, right? When I find the maximum of that, that means I'm considering towards the right side, I mean this part. Okay, so if I draw it like this, four elements are there, and I'm considering the maximum of the minimum two values. What are the minimum two values? This part. Okay, and what is the maximum end of these two?
No,
And
if this is list C, in which
yeah,
we are taking both the elements of list A and list B,
yeah,
then XA, XB, XA1, XA2.
yeah,
I mean, XA2 can come in between XB1 and XB2 as well, no?
yeah. But X, it can be like this, XA1, right? And then let's say XB1, then XA2, and then XB2. This can also be the case. XA1 is the smallest, then XB1 is coming, then XA2 is coming, and then XB2 is coming. Right? Simply. Okay. So what I mean is, so let's say 1, this is 6, this is 10, this is 12. What would happen in the sorted array? It would be 1, 6, 10, 12, right? 1, 6, 10, 12. So XA1 came, then XB1 came. So that's what I'm telling over here. XA1, XB1.
Okay, so by doing this max and min, we are making them next to each
Just
other.
exactly. So see this idea, that's what I was trying to draw. Just see the drawing in this question, in this approach. Drawing is very important. So this is the case. These are the four numbers. I'm not going for X, B, whatever. Ignore all X1, X2, XB, X1. Ignore everything. These are the four numbers. That's it. And these are in the sorted order. Fine. If these are in the sorted order, these two, the first two are the smallest two number, and these two are the greatest two number, the second two. Now what I am telling, see that. So I am considering, you consider the minimum, you take the minimum two numbers. Which are the minimum two number? Now if you check which are the minimum two number, XA1 is minimum, XB1 is minimum, right? I'm considering the minimum two numbers over here, right? And among those two number, I'm trying to go towards the max side, that is the maximum value. So between these two, which side would be the maximum? This value.
Right side, yes.
Right. So I would go towards right side. Fine. Now let's take another color. Now here what I'm doing, take the minimum of the maximum value. Which are the maximum value? These two are the maximum value. What is the minimum? This side. Right. Now I got a blue value and I got a red value. If I find the average, right, I divide it, average. If I find the average of these two, I would get the median. See, that's the idea. Fine. You find the minimum of the minimum, sorry, maximum of the minimum value, you get to this side. You find the minimum of the maximum value, you get to this side again, and then you find the average of this value. So you finally hit this middle line. Okay, so that's the idea. So if you have this is a base case, this would come late. I mean, if you write the algorithm, no one expects to just directly come up with this base case directly, right? This is important. This you should think of your mind when you first try to approach the algorithm, that when should I return the result? The return is when it's of one length, simply return the average, right? But you would see when some list it's working, some list it's not working, because when you are dividing the array, if you get to this a equal to 2, b equal to 2 size, then it is a second base case which is not working accordingly, right? So we take this approach of finding this way, right? This approach. Fine. So yeah, so this idea was very a bit difficult. Code is just what we explained, so it would not take a lot of time. Let's write the code first. So find median, right? Find median. Okay. Again, same, since I have to use many parameters, so let's just call another method. Let's call it median. I'm passing mid of A. Sorry. Middle means I have to pass start from the say, right? The lower value would be 0 and upper value would be length of A. Length of E. Fine. Median. So let's say start of A and let's say end of A. And let's say start of B, end of B. Fine. Okay. Fine. So at first, what we have to do is we have to yeah, we have to go to the middle and then proceed. Okay. Fine. So what would be our approach? The approach is first we would check the middle element, right? The middle value, whether which one is greater, and then accordingly we would proceed. So at first we have to check, I mean, get the middle value. So yeah, let's have the middle value. Let's say end of A minus start of A. So I want to say something.
Middle value for both arrays, correct?
Both. Same thing. I mean,
So an A equal to EA minus SA.
yeah. I'm just making it a little bit differently because I would need the middle later again. So I'm just storing it here in case of B. Okay. I think start of A plus middle. This mid, okay. Anyways, I mean, you just see the code when I need this middle in terms of B also, na? So I would just add that. That's why I kept it separately. So
this we can do because both are of same size.
well, that's the point. Yeah. Otherwise, we would not have done that. Otherwise, this whole thing would not have worked because you cannot assume this middle and that middle would match at the same point. So it would be difficult. So if I have to check the middle of B, right? I have not assigned that. So let's say if that's even, I have not checked as of now the even property. Fine. So my size, if my size is even, then yeah, then my middle would be the average of that. So -1. I would explain just a second. So plus mid and then minus 1. Yes, I would say this in a normal way. It would be mid B equal to the start of B plus the mid. Okay. So that is done. Yeah. Okay. Fine. So coming to this part a little later, it's the same thing, just one or two corner cases would come. So that's why I just wrote it in this manner, because it may be even or it may be odd, right? So you get a minus, just one index error happens sometimes. And that why that happens, that also I would discuss. But yeah, this is very easy. Just I would come to this a little bit later. Let's go to the core part of the algorithm. So base case. Right? Okay, so let's do the recursive case as at first. So since base case would be some if condition, right? What is the first? Okay, let's do it in the base case only. If the size, right, my current size, which is over here, right, the current size n is equal to 1. If the current size of A or B, right, so that's what I'm doing actually. See, I'm calculating the size over here and then finding the mid. Now, depending upon the even oddness, it can be mid minus 1 or the normal mid, right? I'm just taking that. That's why we have this n%2 condition, nothing else. And after that, if n is equal to 1, that is both the arrays are of, now I have reached a point where both the array are of one length, right? I have done, assume that we have done the recursion over here that I would write later. Now this is the base case, right? When both of them are single element. So what did we do? Simply average that out. Simply average that out like we discussed. So I would return the mid is the element, right? So the mid element, or yeah, in this case also is the start element where you have reached the starting point. So simply you return the array which is start of A summed up with start of B divided by 2. Okay. So if the next base case which was equal to 2, right? So here we would just return that the same thing that we wrote over there, max of among the both the array start, right, and with that you sum up with the minimum of the end of A, right, the last element of A and the last element of B. Okay, okay, so this is my max of A plus min of B. This is the array sum divided by 2. Okay, 2 base case done, right? Okay, so what are the left now? The recursive cases, simply elif the comparison, my mid of A, if that is greater than right. So when my middle of A is more, right, so I would consider my array to be the left hand side of A, correct, because the middle element is greater, right? So we move A's middle is more, or so to say A's median would be more, so it's better to move to the left side of A, right? So I call the recursive return, what is the name of the function, median. First is A, B, followed by start of A would remain, but end of A would be up to the middle of A. And B would be towards the, since it is smaller, it would move towards the right side, correct? So its start would be middle of B and the end would be end of B. The other case, when it is lesser, AB. Now A is smaller, so it's better to have A go to the right side, that is middle of A and end of A, and B would move towards the left side, which is start of B and middle of B. Fine, these two are done. Okay, fine. So this is basically assigning depending upon odd evenness, the middle value. After this, this is the this is the one case in base case, the two length base case, and these two are the recursive calls. Fine. Yeah, let's see what. Okay.
Why do we have +1 for n, like EA minus SA plus 1?
This size?
Yes.
Yeah. So EA minus SA, I'm passing. Okay, just a second. Okay. Yeah. Okay, fine. Yeah, so okay, I was just thinking that, I mean, you're subtracting EA minus SA, the index value, so it should be one more, right? The size. So anything you subtract, then you do +1, because I was thinking I have passed this -1 over here, but I did not pass that initially, so that's why the error was come. Anyway, so here I'm passing length A -1, that is I'm basically passing the index value. Okay, and that's why when I'm calculating the size, in my brain I had in my brain that I passed the indices, because this is the start.
Okay, sir.
So that's
Got
why
it.
I add +1. Thanks for pointing that out. I realized that I have not done the -1 over here. Fine. Yeah. So okay. So this is the case. It's working. So basically that's the approach, right? You simply have these two base cases. Now this is a very tricky one. This would not come to the mind very, I mean, yeah, it would not come in the first, or maybe in the first half an hour of thinking, more than half an hour, maybe not in my case, it took me more than 1 hour when I was just first time when I was taking this out, thinking about it. So yeah, so these kind of base cases would turn, I mean, these kind of corner cases would come up. Okay, please don't be bothered about them. You have to just check the output, what are the corner cases where it is not working, and then work upon the code, add more conditions. That's it. But the fundamental idea of how to approach a problem is very important to guess how you should approach. So I hope this is clear. This was also a very nice problem. I particularly like this problem because of this intuitive idea of deciding upon the size of the median, how to go which side. And I prefer to have the intuition in this way about it. Hope it should be clear. If there is some doubt, maybe you can post on Discourse, we can discuss. Fine. And okay, one last thing, that is the fifth question that I want to discuss. Okay, we will not wait for that. Let's go to the fifth question directly. Publish it. Wait, I did publish it, right? I published it. Yeah. Fine. So this is basically median of median. Now, median of median is the idea that I just discussed in the previous case, that you find the median of all the elements, then you again find the median of all those elements, right? You do that and you repeat this step 2 times only works. I mean, you do not have to go further, but if you want in a larger distribution, you may. So yeah, if you repeat these steps, so one thing that you can guarantee is the value that you get, right? That is very near to the median, the original median, but it may or may not be the actual median. Fine. If you continuously find this median of median, so how are we doing over here? If you see this 5 value, so those of you who have seen the lecture, it is fine. Those of you who have not seen the lecture, when you can see this 5 value, na, this plus 5, this 5 value, this essentially means that you are grouping the whole array into 5 subunit, and then finding the median of the 5 subunit, then again median of the next subunit of size 5, like that. You are grouping the whole array into small subparts of each length of 5, and within that 5 length subpart, you are finding the median of that. And accordingly, you would have n by 5. Let's say n is the size of the array, so you get n by 5 units, or basically n by 5 arrays, and you find the median of all of them, so you get n by 5 medians. Right now, among these n by 5 medians, you consider all of this median in an array, put all of these medians into an array, and find the median of that. So basically, you are finding the median of all these medians. Fine, that's what this code is doing.
So the list size should be more than
More than 5, exactly. That's why
more than 5.
yeah, that's what this part of the code is doing. If length of L is less than equal to 5, then you simply do the divide by 2 and return it. That's it. The middle.
So if length is really large, we can choose a higher number than 5 also.
Yeah, you can do that, no issues. But why it is 5, that is the reason which is associated with lecture 5 and 6. I mean, since in the lecture it is taken using 5, that's why we have taken 5 here as well. Fine, you can do that.
Okay.
But why it is 5, that has a reason. You can increase it, but maybe not decrease it. And there is a specific proof considering it is 5. Right. So that I would not discuss. That is actually regarding the so when we use this median of median, it is what it is doing is it is basically giving me the median value of any array, right? The median value of any array, it is giving me in a not median. I mean, it may be median or it may be very close to the median. That is basically I'm assuming it's similar to the median, just like our previous approach, right? It is giving me a value which is very similar to the median, right? In a time which is order of n. So if I'm able to find the median value in an order of, or maybe close to the median value in an order of n time, correct? What happens in quick sort if I set the pivot every time to be a median of median value? That is what is explained in lecture 6 and 5, right? So if you do that, then what you can tell is I can totally bypass the worst case time complexity of quick sort. Even if it is worst case, right? My median of median would set the pivot to be something which is actually the median value, and that's why every time my pivot would place the element in middle, and basically my time complexity would every time be n log n. It would never be n square for quick sort. And also this median of median, extra addition of this median of median code is not causing me extra time complexity because this takes order of n time. Fine, this takes order of n time. Why it takes order of n time? All those things are discussed in the lecture. Yeah, so you first see that. If there is a doubt, maybe in the extra session of week 8 we will
For
discuss.
loop is doing that.
For loop is doing that, correct. But you can see that here we are also having a, I mean, we are going through for loop, that is correct. But anyways, okay, so just see the lecture. There is
Sure, sir.
yeah. Fine. So basically, so what it is doing is it is returning a value which is near to the median of the actual distribution, very near to the median, if not the actual median, in a order of n time. So if I am getting that, I can set as the pivot of quick sort. This value I can set as the pivot, and that basically guarantees me, since it is the median or close to the median, I would every time break the quick sort in a proportionate manner. It would never be the terminal cases, that is where my pivot is at the extreme ends, right? It would never be like that, and that's why I can guarantee it would never be order of n square. So my quick sort's worst case time complexity can be brought down to order of n log n if I use the median of median approach, and this would not cause me extra time complexity because this is order of n time. And quick sort, even if it get reduced, it takes order of n log n. So order of n log n plus order of n is order of n log n. So yeah, that is the basic idea. But here the question is asking you something else. I have not gone through the displayed the question, but basically the question is asking you that if you want to pick a kth smallest element, right? Kth smallest element from the array, a given array, you have to find the kth smallest element from that given array. How to do that? Okay, so that is the question. And obviously your time should be order of n. See, what would be the basic approach? Kth smallest element, no time complexity bar. How would you do that? There is no restriction on time complexity. Simply sort it, right? If you have to find the kth smallest element, simply sort the array, find the kth index element. That's it. So n log n time, right? So it would take you order of n log n time. So in this approach, we are not using order of n log n, we are using order of n time. How would that happen? Okay. Fine. Okay. See, so what we would do is, so median of median is there. So basically what this median of median code would give you, it would give you an element which is close to the median of the list that has been given to you, right? A value which is near to the value.
So it could be either median or one less than median or one more than median in position.
Yeah, yeah, it would be at that, yeah.
Okay.
Very close to the median. Fine. Okay, so how will we do this? How will we do this? The idea is we would use the partition algorithm only of quicksort, nothing else. We would use the partition algorithm. There is only difference is we would change the recursive calls in quicksort, right? We would only change the recursive calls of quicksort. Now what do I mean by that? Just a second. So see, what happens in quicksort is okay, so what happens in quicksort is, let's say I have a distribution of elements. Fine. And let's say I choose this element to be the pivot. Fine. This element is my pivot element. So what would the partition algorithm do? So when I call my partition algorithm on quicksort, what was it doing? Right? So what it would do is it would ensure that any element, if this is the pivot, the one which I just described, right? So any element coming over here, right, in this part of the array after partition has worked, that would be, so if x is the pivot, right, x, so this would be strictly lesser than x, and any element which is over here, that would be strictly greater than x, right? Right. So this is the case. So partition algorithm would ensure this, that is, it would place x. So what does these two things mean? Any element on the left of x, is lesser than x, and any element on the right of x is greater than x. Now these elements are not sorted. These elements are not sorted, but obviously these elements are lesser than x. And these elements are either not, are also not sorted, but obviously they are greater than x. Fine. Now, so what does that mean? That partition is placing the value x in the proper location where it would have been placed in a sorted array. Right? That's the only thing that partition is doing. Partition is placing the pivot element at a position where it should have been there in the sorted array. And in order to do so, it is shifting all the smaller element smaller than x. It is shifting all of them towards the left, and all of the elements which are bigger than x, it is shifting those elements towards the right. Right? Now this is what partition is doing. Now, if this is the case, if in this array my all elements which are left side of x are smaller and all elements which are right side of x are larger, and if I tell you that I want the kth smallest element, provided it has been given to you that k is lesser than x. So k is sorry, not k is lesser than x. I mean, I'm the kth smallest element, right? So what I mean is this index value. Let's say this I is the index, right? I is the index where the pivot x is there. X is the value, right? X is the pivot itself. So I'm not talking about the pivot itself. I'm talking about the value, the index I, where the pivot is placed, right? So what I can tell is if I is the index where x is placed, that means in the sorted array, x is the ith largest element, or if it is smallest, then it is the ith smallest element. So let's say it is sorted in ascending order. If I sort this list in ascending order, then I can say after partition has placed x in a position, I can say x is ith smallest element. Correct? Because it is sorted. Now I am telling you that I want to find the kth. The question is you have to find the kth smallest element provided k is lesser than I. Getting the point? And in the second scenario, this is scenario 1, this is scenario 2. In the second scenario, k is greater than I. So what you can guarantee from this? After I have done one partition iteration, I can say if k is lesser than I, then I only have to search in this part of the array for the kth largest element, kth smallest element. And if it, in the second scenario, when k is larger than I can say that yeah, I have to find only in this part of the array and I can ignore the whole part. This part I can ignore. I only have to search over here. Fine. So that is the basic divide and conquer in this case, that I am I'm not sorting the whole array. What I'm doing is I'm just only one time I'm calling the in one iteration, I'm just having a pivot. That pivot is an arbitrary pivot, right? I'm just placing one pivot initially, and then I'm trying to find if that pivot is the ith smallest element. I can guarantee, since pivot partition algorithm has run, that pivot is in its proper location. So if it is at the ith index, so I have total I elements before it. And if my k value, the kth smallest element, I want to find, if k is lesser than I have to find on the left side of the array. If k is greater than I have to find on the right side of the array. But the problem in this approach is, again, if I choose this pivot very badly, and this pivot is the extreme right element, right? So again, this would take me order of n square, like in quick shot, because we are simply applying partition same way. But since now I have the median of median, I would choose the pivot to be the median of median element. So this pivot that I chose arbitrarily over here would actually every time be chosen to be the middle element over here, somewhere over here, right? And then I would have my I over here, and depending upon k is lesser than I or greater than I would check over here or over here. Everything is same. I'm just using the median of median, and I would put them in the partition method, partition algorithm. Only one change that is there with respect from quick shot, and that is here we are finding the smallest element, kth smallest element, not sorting the array. So I need not go to all, I need not iterate through all the iteration of quick shot. So what was the condition of quick shot? If beginning is less than equal to end, right? Then what did you do? I'm just writing a pseudocode. If beginning is less than equal to end, then you had some index k equal to partition, right? Partition whatever a dot dot start end you passed, and then you simply called quick shot of the array from start to k minus 1, and again you called quick shot of the array from k plus 1 to end. This is quick shot, right? But here I do not have to sort the array. The very moment I get my kth smallest element in the process, I can quit the process, right? I can quit the recursion. So this beginning less than equal to end is something which is not required to have. I mean, I do not have to reiterate through all these steps. Okay. So what I would rather do is, and also I do not have to iterate through both the subparts of the array, because I told you that you can ignore depending upon the k value and I value, depending upon these two conditions, I can ignore one part of the array, either left or right. So like in quick shot, we used to do both the areas because I have to sort both sides, correct? So I used to call quick short on both the halves. Now I do not need that. So what is the modification that I need? The modification is that K and I condition, right? Here we are discussing this K and I condition. This K and I condition, correct? This K and I condition we are discussing, and here we have not used that. We have to somehow implement that. Okay. So one small change here, actually it should be I according to our concept. Okay. Fine. So yeah. So what is the change that is required? So either this or this, only one subpart. What is the condition that would decide which subpart to go? This condition between K and I. So I simply write that if my, what would be the condition? If my the kth value, right? The K value, if that is lesser, right? You go to the left side, that is we call the start I-1 index. Quick short start to end I-1. If K is greater than I, then you call quick short on I+1 to end. That's it, nothing more. So let me go to the code first and write it. Acha, one important point, where are we actually finding the element? So these two are done. This is, I am going to the left side depending upon if K is lesser than I, you do that, or if K is more than I, if K is more than I, you do this, the second way. But when are we actually returning the location where I have found K, right? I have to return that index. So that is not done. Here we are just iterating through. So how can we do that? We have to add one more extra condition when the value would match, right? And that would be my end. So that these all are if. If so, what would be that case? That case would be when the kth value, I mean the value K and I are same. Basically, you have reached at that point itself. Getting the point? That is your you would return the low value when it is equal to that value. That is your K is equal to 1. That means what? Your pivot is itself the value that you are trying to search, right? And it has been placed at the proper location. And if K is equal to I means what? What was I? When I was running the partition algorithm, I said this means what I can be sure about is once I have run partition and partition has placed X, the value X at the ith index, that means the proper position of X is is at ith index in the sorted array. Alternatively, X is the ith smallest element. Now, when I am saying I is equal to K, if this is true, what does that mean in this statement? I is equal to K, right? So what does that mean? X is
It
K
becomes
smallest.
the kth.
So that's what you want to do. You have to find the K smallest element. So this is the core idea behind this. Let's quickly go to the code now. I will do that. Fine. The analysis part of it, I would request you to just watch the lecture, and if there is any doubt, please comment in Discord. We would answer. And maybe in the week 8 extra session also that we are planning, we would discuss the last 2 lectures. But this is exactly the code which has been discussed in the last 2 lectures. Okay. So okay, finally let's see kth smallest. Array is there. K value is there. Right. Okay. So kth smallest. Smallest array K. Okay, so what are the things that I need? It would be quick short with just the recursive cases would change. So basically it would be quick short, right? So if then let's call this function quick select, maybe k select list I would need, and yeah, it's quick short, so lower upper and size, that's it. Okay, so low, right, up, okay, index. Fine. So k smallest, I have to call this k select. Okay. Now that array and 0 up would be my size and the key. Okay, so now let's start up. Let's start it. First, I have to check the median of median code, right? It is okay. Then I have to check the median of median at first, and then change it with the pivot. Okay. See, so what are the things that we would do at first? Just do step by step. First thing is, at first, let's do the overflow check. So if, sorry, underflow. If my k value, if that is lesser than anything, I mean one value, right? Or my k value is greater than, let's say, the out of side upper limit minus lower limit. Why up minus low we are doing? The reason for that is, in the first instance, up is enough. That is, if the kth smallest element is out of index itself, right? So if that is the case, then it is okay. I mean, I can just write up. It's out of index. So then I would return nothing. But the thing is, in the subsequent iteration, since k select would happen recursively, right? Like quick sort. So in the subsequent iteration, this, I mean, in the subparts of the array, it would not be greater than up only. When I'm considering a subpart, I have to consider the upper limit corresponding to that subpart, right? So I have to incorporate the lower as well, because in a subpart, the lower would change, right? So that's why we are doing up minus low. So if k is greater than up minus low, it is greater than the length of the subarray, or it is lesser than 1. In that case, what are we doing? We are simply returning none. So that was the sanity checking. After that, I have to get the median of median, the first pivot element, right? So I just store pivot equal to the median of median, and I'm passing the array. So again, same thing. If I pass like this, the normal array, right? I'm finding the median of median of the code, but I cannot pass directly L. The reason for that is, again, the sub array. Every time I'm calculating the median of median for a sub array, it would not, I mean, L would be passed every time, right? That is not something that I want. I want to have the median of median corresponding to that sub array. Correct. So in that case, I have to pass the sub array actually. So how can I get the sub array? Any sub array is low to up. So simply pass low to up. Fine, that is done. Then pivot. Now I do not have the index, right? Pivot index equal to, because median of median is returning in the pivot itself. So I have to find the index of that. Now here the pivot index, how would I find? I told you the median of median is a close approximation of the median. It may not be the exact median. Fine. So what are we doing is, since it is close approximation, we would find the closest element to the value that we have. Value means the pivot. We would find the closest element which is to the value of the pivot. But also we do not have the index, because see, median of median, maybe let's say in the distribution, what I mean is, let's say in the distribution, I mean, you have a distribution of, let's say 1, 2, 3, 4, 5, dot up to say 1000. Fine. Yeah. So maybe this is your distribution. Your median would be something around 5, not something, it would be at 500, right? But let's say median of median has returned you 500.25. Okay, let's say in the distribution, your median of median has returned you 500.25. Now this is the value which is returned by median of median. It's not an index or anything. And also it is not an element in the list as well. It's just a value which is closer to the original median of the distribution. Okay. So what I would do is I need to find the value which is closest to this value. Fine. And in that, and that's why I'm using the minimum function. I would use the minimum function over here. Okay, let's see. So first of all, I would have a list in which I would store, let's say for I in is equal to my pivot. Let's say if this is the equal value, in that case what I would do, and then I'm finding minimum. Oh. Okay, so every time you may not get the equal, or every time you may get an element in a, sorry, sometime you may get an element within or without. Sorry, what I mean is many a times you would get an element within the distribution, or at least you would get it closer to the distribution, closer to the median of the original distribution. So you can judge from there, right? Okay, so that is done. Now next thing is what, since I've got the pivot index by doing this, only thing that I have to do is now simply set the pivot to be the, I mean, in the our implementation of quicksort, the
one thing, this MOM will, you said it will return a value which is closest, which could be closer to the median or the median itself.
Yeah, or
But
means closest means it can be itself in the list also, right? In this implementation, it is actually in the list itself. But the original median of median theoretical concept, when you see, it may be closest. That means it may not be in the list also.
that was my query. So so
Here,
if it is in the I mean a list element, then it is okay.
Yeah. In this implementation, na, just a second.
If you are speaking, you are on mute.
Can you hear me?
Yes, now we can.
Okay. Yeah. So what I was saying is, here in this implementation of median, see, we are actually iterating through the list itself over here, and I'm just moving it by updating the incrementation of the list by 5, and then we are simply returning this, see, x of length x by 2. So length x by 2 we are going, but we are returning it as the index value. I mean, I'm returning as the x of length x
Element of the x. Yes.
But conceptually, when you do in the theoretical concept, when you actually check for median of median, even when you do not have a list or array, simply taking the median, then again calculating the median, like the same concept we applied in the previous case. There we did not have a specific median. We were only deciding whether I should go to the right side or left side by checking the greaterness of the median. I mean, which one is greater or which one is lesser. We are not exactly checking with equating. So yeah, so that in case of median, basically you would get a nearest approximate value. But in this implementation, since we need this condition to be applied, right? So here we are actually returning this right x of that, and that's why we can be ensured that this returns a value which is inside the list, closest and inside the list. Fine. Okay, so yeah, and one more thing. So let's say if the distribution is very sparse distribution, and it's not important with respect to the code, but since this has come up, I'm just discussing. So if this is a sparse distribution, right? So it may be the case that I mean, the thing that you told that your pivot, sorry, your original median would be maximum +1 or -1 from the median returned by this median of median algorithm, right? If it is a sparse distribution, why? Because if it is sparse, then there are not multiple value between the original and the duplicate, original median and the median returned by my algorithm. If it is parsed, because the values are spaced out. But if it is a dense distribution, right, there are many values between two data points. In that case, it may not always be the very -1 or +1 index. Getting the point, because it depends on the, I mean, the weightage of the value. So let's say
Yes, there could be so many in between as well.
small, yeah, and let's say most of the elements are very small. So let's say your median returned by this algorithm is 512, and the actual median is, let's say, 508 or something, 509 or something, 8, let's say 508. Okay, and you have very small values, 509, 509, 510, right? All of these are there. Or maybe you can have a large, you do not have 509 or anything, you have direct 508 and then 512. Getting? So in that case, you get the next index to be the actual median. But if you have densely distributed values, in that case, the next element may not be the I mean the median, the actual median. So it is better to use a minimum function to calculate the first index which you get, where you get the median value. Okay, fine. So okay, so anyway, those are intricate things, not required. Basically, we are finding the median, and now we are just swapping the median to be the pivot, and then call the partition algorithm as it is. So let's do that. Let me swap it. So L of the, since in partition algorithm we consider the first element as the pivoting element, right? So I would just swap the first element with my newly found pivot index. So I can then ensure that the pivot that my partition algorithm would start working on, my that pivot would be the median, and that's why I can guarantee always my n log n behavior. N log n behavior in case of quick shot. Here we are doing something else. So let's see. And I hope you understood that why we are actually getting that difference from quick shot, because in quick shot we called on both the subpart. Here we would only call on one subpart, depending upon whether my k is greater than or lesser than the I value. I mean the pivot index in this case.
Yes, we are discarding one part.
Yeah, exactly. So let's write the code now. So if my LO swapping, right? Yeah, so I'm swapping with my pivot index. Okay, so now swapping is done. Now let's normal partition algorithm. Okay, so okay, since we are kind of out of time, let me just copy paste the partition algorithm from somewhere. Anyways, I'm not getting it. Okay, fine, I'm just writing. So pivot lower I need the next, right? So low plus 1 and up plus 1. No, upper low plus 1. Sorry. Fine. So this is done. Then fine. I have to check now whether the element I is greater than the pivot. If it is so, I change my up equal to up plus 1 or up plus 1 or else I change the my low with the ith element. And also I change my lower and upper. So low up equal to low plus 1 and up plus 1.
In line number 20 also, we should be doing up plus 1.
No, lower and upper was there. Both of them would point to the element just after the pivot. After that, low would proceed up would proceed one by one. I mean this one, upper. This upper would proceed one by one. Okay, here why I have written low? Sorry, here it could be lower. Here it is low, fine. Yeah, fine, range is fine. And lower, this is lower, this is upper, this is lower, this is upper. Yeah, so this is basically both would be low because you are just at the index over here in partition algorithm. So let's say 1, 2, 7, 8. So if this is the case, and let's say 9 is my pivot, right? So what would you do? You would place your low and up, your lower and upper both at 1, both would be at 1, right? And then you would move this upper one by one you would move. Whenever you see a value which is greater, then you stop it and just replace it with the lower, and then you increase both lower and up, right? So that's how you do it. Sorry, not greater, lesser value. So both would start from the next element of the pivot. So that's why both are low plus 1. So here I'm doing low and lower. Two are there. Low means this out of the main, the main iteration where iteration happening, the k select loop, and lower is just for this select of this partition algorithm. So if if you just recap from quick shot, this part is your partition algorithm. I have not finished it, but this part is the partition algorithm. Line number 22, plus. So yeah, lower and okay. So we have just swapped the values and then we have updated the indices, right? And otherwise, I'm just moving. Oh, this is upper by 1. Upper plus 1. Okay. Yeah. So finally, we have to just swap the last pivot with the low value. So low and my so my algorithm is ending at lower, right? Lower plus 1. So that means the last element which has been swapped is at lower. So I have to check with lower value. So lower minus 1. Okay, equal to lower minus 1 and low. So final swapping is done. Okay. And yeah. Okay, so this is your partition, normal partition algorithm. If anyone wants to just refresh it, you can refresh. But this is the normal partition algorithm. Okay, so now this is the different part. This is your partition algorithm, right? This is simply I'm using the median of median to get the pivot and then finding the index of the pivot. Once I find the index of the pivot, I am just swapping the low element with the pivot, right? So that the partition algorithm, which I have written over here, it always starts from low, right? See here, the pivot is the low. That's how we have done the partition algorithm in quick shot. So since it starts from the low, I am just ensuring that before the partition start in line number 18, I am swapping the median element with the low element, I mean the first element. So that whenever partition starts with this low is basically my pivot index, which is my median element, and I can guarantee that the pivot now, this partition algorithm is working on a pivot which would be the median one. Since it is the median one, I can get a better complexity, right? I would not get into the worst case. So now let's come to the normal quick short recursive part. So this was the partition. Now is the recursive part is one thing that we have to discuss. Also, we have since we have placed one element, so that step I forgot. Not lower, so that should be my no, yeah, lower only. Since I have since I have placed one element, right? My pivot element is now placed by the partition algorithm. It is placed at a particular index, and that index is the lower index. That's what we are doing here at lower. So since it is now placed at a certain position, now I am checking for the element before it and after it, right? The two subparts. So that's why I am reducing the size by 1. Okay, and this size should be my lower. Okay, yeah, this would be required later. Fine. Yeah, so this side would be my lower size. Fine. Yeah, so that's why I'm reducing the size by 1. Okay, so now let's see. The next is the recursive part, the main quick short. I mean the quick short code modified. What is the modification? Only in the recursive call that I'm calling on one side. So that thing we would do. Okay, so if my k value, right, if my k is less than equal to the lower it should be lower. I am placed one element, so size got reduced by 1, but the kth element it should be okay. No. So no, not lower. It should be my lower minus low. Right. Okay, wait. Okay, so let me just tell one thing. So see, in the before starting the quick shot, we have to just discuss one small thing. So we might be moving into the subparts of the array, right? In the left or right, or I mean, in any of the subpart. Now, which is the point where I have? I mean, what is the index where I have placed the pivot? Lower, correct? That's why I'm swapping, right? That's what I'm
Yes.
sure. So lower is the index where I've placed. So now I am just, if lower is the index where I have placed it, and I assume now I am in a subpart of the array. So how can I get, I mean, how can I get the length, right? Lower is the in. So what I mean is, just a second. So let's assume this was my array.
Lower minus 1 will be left
Very good.
subpart.
Not minus one. Minus what? I want the length. I want the length. So what I mean is, just a second. So if this is lower, right? This is the point. This is the element where I have placed my pivot. So this is lower, right? And so what are the two subparts? This is one subpart and this is one subpart. Correct. So I want to go over here. Assume that I'm going over here on the left side. So let's say if in this case my k is smaller than I, so I'm smaller than lower. I means I is lower here, right? I is nothing but lower. I means this I, the I that we discussed while discussing the concept. This I.
Yes, sir.
So that is lower, right? So let's assume that I'm going towards the left side. So in that case, what would be the length of this part? It may seem that it should be lower itself, because basically lower minus start index is 0. So lower minus 0 is lower. But this may happen in subpart of array as well, right? So what happens if the subpart is up to here, like this? This is the subpart, right? And my index, I mean,
Yes.
the pivot, correct.
Difference.
So this is the pivot where I have placed. So this is my lower. So now if I say I have to go towards either of these two parts, either this is one subpart or this is one subpart, correct? So how can I get this subpart? I mean, what is the length of this part? It should be what? Lower minus the low value. This value is low, right? And this is high. I mean, fine. So if you go to the code, what was the low and up? Who was keeping track of low and up? This low and up, right? Not lower. I should have used another name, but anyways. So this low and up is the subarray top and bottom. That is low and up of the subarray. And here lower and upper is basically the two markers that we are using in the partition algorithm. So these are just lower and upper are just the markers. These lower and upper partition markers. Okay. So I have placed the pivot at the proper element at the lower index, that is at the marker, lower marker. Now, so I have to just, before moving into the recursive call, before going into the subparts, I have to confirm which is the length of the subpart, right? How can I go to that part? So that's why we have to, let's say length equal to lower. Why I am telling this? I'll just come to that.
If k is less than lower.
That I would come to the next part. Why is it giving error? Okay, indentation. Okay, so now the if condition, if k, that is the, that my k value, if that is less than equal to, let's say lower, I mean the length that I got. What does this mean? That is the value which I got on the, I mean my k value, the kth largest, right? Kth largest. Now, if that kth largest, the kth value is smaller than the in this length value, right? So what can we understand from that? That is what are you getting? That it is towards the left hand side, right? If I get it over here, if I come see what's happening, if I say this is the length, right? This is the length, which is basically length, right? And if I say the kth index in this case, the kth largest value, smallest value, something that we want, right? K smallest value. So if I say k is less than length, that means what? That means my value should be in this part of the array. This is my starting point, this is my ending point, right? So here, there we used to write in the previous, in theory example, in the theory explanation, we wrote if k is less than I. Why we could write k is less than I? Because here we were considering on the whole array, not on the sub part. So that there is a hidden something over here. What is hidden? K minus 0 is hidden, is less than I minus 0. Right? So this 0 is basically the lower limit of the sub array. Okay, otherwise in next iteration you would not get the correct result. Fine. So that is what we are doing. So now k less than length means so I'm going to the left side. So just bear with me. When I write the last statement, when I would modify the k also, you would understand why it was written like that. Okay, so what was the function name? K select, right? Okay, let's discuss this slowly, and because this is what mainly we the lecture 5 and 6 is about mostly. So okay, k select, and I want to pass the parameters which are low, up, and k, right? Now see, I want to move towards the left side. So what should be my start value? Low value, because what is the start? This is the start, right? Subpart starts over here, which is low, right? If you see this k select low, because every in the argument list where I have this in the argument list of this function, the low and up means the low and up of the sub array. Okay, so that's why I want to start from the sub array. Every time you work in a recursive code, always think of the sub array. So I want to move left side means the starting index is the start index of the sub array. So low.
How I say is that in the list provided as a parameter, we are demarcating low and up. May not
Exactly.
be and may not be the ends itself.
Exactly. So that was just the concept. When we discuss the concept, that is the main idea. Now, when you code it, you have to think of the subpart, what will be the variable values and all that. That's it. The main thing is same. So, okay, so it would be up from low to the upper limit of the subarray. What was the upper limit? This was the upper limit, right? Left side you want to go. So
Lower.
this is lower. Okay, so lower and passing the k. Now, let me just take another small example over here. See, in a distribution like this, fine. I am telling you, I need to find the third smallest element. Okay, I need to find the third smallest element. So you divided the array into two halves, let's say. I mean, according to this approach, you divide the array into two halves by partition, and you fix this pivot 4. I mean, the partition algorithm would fix the 4 as the pivot because we use the median of median, and 4 is kind of the median. Suppose 4 is the median. So it fixed 4. Okay. And after that, since it fixed 4, what is lower over here? Lower is this value, the value corresponding to 4. This is my lower. Okay. And I want the third largest value. So that means I want the third largest value, and 4 is at index, index equal to 3 basically. So basically I have to move towards the left hand side because it should be at my third largest value should be at index 2, correct? Third largest means what? Sorry, why I'm saying largest, smallest. So third smallest means what? It would be at index 2 in the sorted sequence, right? Arbitrarily this is actually the sorted sequence, but okay, in the sorted sequence it should be at index 2. So, and I am now, my lower is at index 3. So I'm sure that I must go towards the left hand side. That is what this if condition is all about, right? So in this case, see, one beautiful thing is my k was what? K was third largest element, right? K was 3, third largest element. So when I move to on the left sub part of the array, still my k becomes largest element, because when I operate on this subarray, k is still third sub largest, the third smallest element. Why I'm saying largest? No? Pardon me, third smallest element. So it is still valid, and I would calculate 1, 2, and third 3 is the smallest element, third smallest element. Okay, but in the same distribution, I mean, this is quite trivial, but now you would understand why I am discussing this. Same distribution, consider something towards the right side of the array. So 4 is again the same pivot which has been fixed. So this is my lower. Okay, but now the question is, I want to find the seventh largest element, seventh smallest element. Okay, seventh smallest element I want to find. So when you see lower is equal to 3, and I know since k is 7, that is I want the seventh smallest element. The seventh smallest element should be located at index what? At 6. We know in a sorted array, any kth smallest element would be located at k minus 1, index k minus 1. So I see lower value is 3, and I want the value of index to be 6, right? So this is not the proper place. So I must go which side? Right side. Same condition, this condition. I mean, I'm sorry, just the opposite, this condition. Now you see, so when I go in the subpart, right subpart, so what is the right subpart? Let's write that. What is my right subpart? Now see, this is important. Huh? Right subpart is 5, 6, 7, 8. Correct? What was k? K was seventh largest, seventh smallest element. If I pass in the algorithm seventh smallest element,
Out of index.
Out of index. Correct? So what has to be done when I'm going away on the right side of the pivot, right? When I'm on the left side of the pivot, I'm anyway going towards lesser value. So I do not have to reduce anything. I mean, k smallest would be on left side only. But when I'm going towards the right side, I'm skipping all this value. I'm skipping all this value. I am eliminating them. So I have to also eliminate the, so the count of the value that I reduced, I have to reduce that from k as well, correct? Otherwise,
A minus lower.
exactly. So when I am calling the next iteration recursively, when I go to the right subpart, right? When I'm calling the recursive call corresponding to the right subpart, left subpart recursive call is okay. Right subpart recursive call, I have to modify the value of k. So this is left subpart. So that's why I kept k as it is. Right? Now let's go to the right subpart. Okay. Acha, before going to the right subpart, let's draw the base. I have the base case. So what is the base case? When k is equal to the index that you actually got. Right? I mean, so basically your k is equal to it is, I have done -1 over here, right? Because it is getting reduced, but last swap was at lower. So I have to check k with the lower value. So I would do +1 now over length, sorry, my low length, because length is dependent on lower, and lower after swapping we did -1 because we have placed one pivot element. So the total number of element minus the pivot element, that is the count of the rest of the sub arrays, right? Total elements left. So that was required over here. And now here I have to check whether that is the index or not. Since it is the index, I would add 1 just to balance that. Okay. So so basically this means I equal to k, that part, that condition. So if this is my case, I would directly return my value. Okay. Return L lower. Yeah. So the element that I'm getting over there. Yeah. Fine. Now the right subpart case. What is the name? K select. array. Now I'm going to right side. So lower would be what? I would add the, I would, yeah, I would go to the right side, right? So first thing is that I have to pass is
Lower plus 1.
correct. So here it was up to lower. Now I'm going to lower plus 1. And then the upper limit is same, no problem. So that would be up. And now we have to pass k. Now we discussed that I have to subtract the element which is there in the left side, right? So I would subtract that, and with the element which is there in the left side, I have to also subtract plus 1. Subtract one more. Why? Because the pivot also I have ignored. Correct. So we are doing lower plus 1. That means we are moving away from the pivot. That's what we do in quick short. I call quick short from beginning to k minus 1 and k plus 1 to end. So that pivot itself also I have to subtract from k, because that is also, one element. So I would do k minus my okay. So now what I would do here, I have so all those elements I have to subtract. Now this subtraction is also happening in the sub array, right? In any sub array. So what is the length of the sub array that we got? This one. Remember we discussed this, the length of the sub array on the basis of which we are discussing. So this is that value. So we would subtract that. Okay. So length. Okay. And for the pivot itself, plus 1. Okay. So I may be wrong in some of the boundary condition. I don't know. Let us check. Fine. So
Length plus 1.
for the index, na. So when you do minus, so when I'm doing minus, so when I have calculated length, what was length? This part, correct? But when I'm going to the right
Actually,
side,
length was okay. Length was without pivot.
yeah. So
So
we have
length
to
plus the
yeah. So we have to consider up to the pivot over here, not up to here, up to here. So plus 1 was for this pivot itself, because I'm now going for this part, right? This part. Sorry, this part. So for the pivot, plus 1, the pivot element. Okay, so here I have decreased 1 because my lower is required. Then I'm calculating the subarray length. Subarray length is lower minus low, and k less than.
this length we are calculating when we are going towards the left subarray.
Length we are calculating anyway, right? Because see, here we were working with I and k in this example, but that's what I discussed now, because k minus 0 and I minus 0 was there. Actually it should be k minus low, I minus low, because in subarray your low would be the length actually, correct? So that is what we are doing in length. Otherwise every time I have to write over here k minus lower minus low, then k minus lower minus low.
Correct.
So I have stored it in a variable.
Yes, so this length is the length of the subarray which is towards the left
Correct.
of the pivot.
Correct, exactly. I'm just checking whether okay, so minus 1, then lower k. I've done okay, k equal to length. Fine. Then length plus 1 is there. Okay. K is equal to length. Okay, so yeah, the pivot element, if that is equal to k, fine. Then I'm returning the last total. Yeah, fine. Okay. Okay, I hope it should work. Let us see. Basic idea is okay, fine, fast, great. Basic idea is same, but due to this minus 1 plus 1, there can be sometimes something is running in your mind, you can mess up with the index and this value. So you just have to check those corner cases sometimes. Yeah, but fortunately it worked fine. yeah, so this is the basic question. If this median of median theoretical proof is something that you have to check in the lectures, but if you have understood this coding, I hope the 5th and 6th lecture would not be that much difficult, at least from the coding point of view. Fine. Okay. Okay. So thanks everyone. It took quite a lot. Yeah. Check the lectures and then please again try to go through the codes. I hope it would be helpful. Fine. So a few more questions are there in the replit. I'm just one of the. This was the main question, the one that we discussed. Other two are quite easy. You all can check that. Fine.
No, I think you have not published them.
I have not published.
Have
I'm
you?
just making. I'm just publishing. One question more is there. So 3 questions we discussed. Yeah. You have published. Okay.
If you have.
Thank you. Thank you, everyone. Okay. Good night.
Thank you.